Before industrialization, production systems were embedded directly within local environments and social structures. Economic activity was shaped by land, climate, population density, and inherited custom rather than by centralized planning or distant coordination. Households, workshops, and small communities produced most goods close to where they were consumed. The separation between producer and consumer was minimal, both geographically and socially. Tools were simple, energy sources were organic, and output volumes were constrained by human and animal labor. Production rhythms followed seasonal cycles rather than clock time. Exchange occurred through personal relationships, local markets, and customary obligations. These conditions created supply systems that were resilient at small scales but limited in reach and flexibility. Goods moved slowly, information moved slower, and coordination relied on trust rather than contracts. What existed was not a global supply chain, but a mosaic of localized production systems loosely connected by trade routes. Agricultural production formed the foundation of nearly all pre-industrial economies. Most populations were engaged directly in food production, and agricultural surplus determined the capacity for specialization elsewhere. The mechanism was straightforward and restrictive. When yields were low, labor remained tied to subsistence farming. When yields improved through irrigation, crop rotation, or soil management, some labor could be released into non-agricultural crafts. This worked because food storage enabled delayed consumption, allowing producers to survive between harvests. Grain, dried legumes, and preserved foods functioned as early logistical buffers. At the time, transport costs were high relative to value, so surplus rarely traveled far unless it could survive long journeys. Regional differences in crops shaped trade patterns and local diets. Agricultural constraints therefore set the outer limits of early production networks and defined how far supply relationships could extend. Craft production developed within this agricultural framework and remained closely tied to household organization. Artisans worked from homes or small workshops, often combining farming with skilled labor. Textiles, metal tools, pottery, and wood goods were produced using techniques passed through apprenticeships rather than formal instruction. According to historical records, medieval European guilds regulated quality, pricing, and training within urban centers. These institutions reduced uncertainty by standardizing output and protecting local markets. Studies show that guild systems limited competition but increased reliability for buyers. Production volumes were low, but consistency mattered more than scale. Similar structures existed elsewhere, including caste-based crafts in South Asia and workshop clusters in China. Each system balanced specialization with local control. Supply chains at this stage were short, predictable, and deeply embedded in social regulation rather than economic abstraction. Long-distance trade introduced complexity without displacing local production. Luxury goods such as spices, silk, precious metals, and fine textiles traveled across continents through layered exchange networks. By the first millennium, caravan routes across Central Asia and maritime routes across the Indian Ocean linked distant producers and consumers. At the time, no single actor controlled the full journey of a good. Merchants specialized in segments of routes, handing goods off through ports, markets, and intermediaries. This worked because risk was distributed across many participants. Losses from theft, spoilage, or political disruption were absorbed locally rather than system-wide. The mechanism relied on redundancy rather than efficiency. Goods changed hands many times, accumulating cost but also resilience. These early trade networks expanded awareness of distant resources while leaving core production structures intact. Transport technology imposed strict limits on scale and coordination. Roads were uneven, ships were wind-dependent, and pack animals carried limited loads. The reason distance mattered so deeply was that movement consumed time, labor, and resources without increasing productive output. According to archaeological studies, inland transport costs could exceed the value of bulk goods beyond short distances. This meant supply chains favored high-value, low-weight items. Bulk commodities like grain moved primarily by river or sea when possible. Infrastructure investments, such as Roman roads or canal systems in China, reduced friction but required centralized authority to maintain. Even then, capacity remained constrained. These limits discouraged centralized production and favored dispersed systems adapted to local conditions. Coordination across regions remained episodic rather than continuous. Information flow shaped supply behavior as much as physical movement. News of harvest failures, price changes, or political instability traveled slowly and unevenly. At the time, merchants relied on letters, messengers, and personal observation. This delay created persistent uncertainty. Producers could not easily adjust output in response to distant demand signals. Instead, production decisions were based on tradition, experience, and local expectation. According to economic historians, price convergence across regions occurred gradually and incompletely. Markets remained fragmented. This fragmentation reduced exposure to distant shocks but also limited responsiveness. Supply systems therefore emphasized stability over optimization. Adaptation occurred over generations rather than seasons. Labor organization reflected these constraints and reinforced localized production. Most work was manual, skill-dependent, and learned through direct supervision. Division of labor existed within workshops but rarely extended across regions. The mechanism was social as much as technical. Skills were embedded in people rather than codified processes. This worked because communities valued continuity and reliability over rapid change. According to studies of pre-industrial labor markets, mobility was limited by legal status, family ties, and custom. As a result, production capacity could not be rapidly expanded or relocated. Supply systems absorbed shocks through consumption reduction rather than output scaling. Flexibility existed, but only within narrow bounds defined by human endurance and social norms. By the end of the pre-industrial period, production systems had achieved durability rather than speed. They persisted for centuries with incremental change rather than transformation. Trade connected distant regions, but production itself remained rooted in place. These early supply arrangements prioritized survival, continuity, and social cohesion. They created the baseline from which later industrial systems would diverge. Without centralized coordination, standardized components, or mechanized energy, supply chains remained organic and human-scaled. Yet they established essential patterns of exchange, specialization, and trust. These patterns would not disappear with industrialization. They would be restructured, expanded, and abstracted, but their underlying logic continued to shape how goods moved across societies. Pre-industrial supply systems were sustained by institutions that stabilized exchange in the absence of modern coordination tools. Markets were periodic rather than continuous, often operating weekly or seasonally. These markets served as aggregation points where surplus goods could be redistributed beyond immediate households. Prices were shaped by local conditions rather than global signals. Authority figures such as town councils, temples, or royal officials frequently intervened to regulate weights, measures, and acceptable pricing ranges. This worked because trust was fragile and easily undermined by fraud or scarcity. According to historical studies, standardized measures reduced disputes and improved repeat exchange. Market rules substituted for formal contracts by embedding expectations into custom. Enforcement relied on reputation and communal pressure rather than courts. These mechanisms allowed limited scaling of trade without requiring centralized logistics. Supply chains remained shallow but socially reinforced. Money played a partial and uneven role in these systems. In many regions, barter, credit, and obligation coexisted with coinage. The mechanism was adaptive rather than uniform. Coins facilitated trade where strangers interacted, but within communities, accounts were often settled through delayed reciprocity. This worked because long-term relationships reduced the need for immediate settlement. According to economic historians, medieval peasants frequently carried balances across seasons rather than paying at each transaction. Credit linked producers and consumers across time rather than space. This temporal flexibility softened shocks such as poor harvests or illness. However, it also limited expansion. Credit systems were personal and non-transferable. They could not easily support long-distance supply coordination. As a result, money enabled trade density locally while leaving broader supply structures unchanged. State authority influenced production indirectly through taxation and extraction. Rulers demanded surplus in the form of grain, labor, or goods rather than abstract revenue. By the early empires of Mesopotamia, Egypt, and China, bureaucracies recorded inputs and outputs to support redistribution. At the time, these systems functioned as proto-supply chains for armies, temples, and construction projects. According to archaeological records, grain storage facilities acted as centralized buffers against famine. This worked because states could compel contributions and manage stockpiles. However, these systems were limited to political centers and did not restructure everyday production. Most households continued producing for themselves first. State logistics operated in parallel rather than replacing local supply systems. Their influence expanded reach but did not standardize production across regions. Environmental variability imposed constant pressure on pre-industrial supply arrangements. Weather fluctuations directly affected output, transport, and labor availability. The reason resilience mattered more than efficiency was that shocks were frequent and unavoidable. Droughts, floods, and pest outbreaks could collapse yields across entire regions. According to climate historians, multi-year crop failures were recurring features of pre-industrial life. Communities responded by diversifying crops, maintaining seed reserves, and relying on kinship networks. Trade could alleviate shortages, but only when routes remained open. This uncertainty discouraged heavy specialization. Production systems favored redundancy over optimization. Supply chains therefore absorbed volatility through social adaptation rather than technical control. Urban centers introduced higher degrees of specialization without breaking pre-industrial constraints. Cities concentrated artisans, merchants, and administrators in dense spaces. This allowed finer division of labor within crafts such as textiles, metalworking, and construction. The mechanism was spatial proximity. Producers could exchange inputs and outputs quickly within city walls. This worked because short distances reduced coordination costs. According to urban economic studies, medieval cities increased productivity through clustering effects. However, cities remained dependent on surrounding rural areas for food and raw materials. Urban supply chains extended outward but did not replace agrarian production. Cities intensified demand without fundamentally altering how goods were produced elsewhere. The system remained balanced between concentration and dependency. Maritime trade offered greater carrying capacity than overland routes and reshaped certain supply patterns. Coastal and riverine transport reduced per-unit costs and enabled movement of bulk goods. By classical antiquity, grain shipments supported large urban populations such as Rome and Alexandria. At the time, maritime logistics required predictable winds, seasonal scheduling, and port infrastructure. According to historical shipping records, Sailing calendars governed trade timing. This worked because coordination followed natural cycles rather than continuous planning. Risks remained high due to storms, piracy, and shipwrecks. Insurance mechanisms began to emerge to spread losses. These developments increased scale but did not eliminate fragility. Maritime supply chains expanded reach while remaining exposed to disruption. Knowledge transmission shaped production quality and continuity. Techniques were preserved through oral instruction and demonstration rather than written manuals. The reason this mattered was that processes could not be easily replicated elsewhere. Skills traveled slowly with migrating craftsmen. According to studies of medieval technology diffusion, innovations spread unevenly and often stalled. This limited standardization across regions. Production outputs varied in quality and specification. Supply chains therefore adapted to variability rather than enforcing uniformity. Buyers adjusted expectations based on origin. This flexibility supported exchange despite inconsistency. It also constrained integration. Without codified processes, scaling production across locations was impractical. As pre-industrial systems matured, they achieved equilibrium rather than growth. Production matched demographic and environmental limits. Trade connected regions but rarely transformed core structures. These supply arrangements emphasized continuity, predictability, and social embeddedness. They created enduring patterns of exchange that survived political change and technological stagnation. The absence of mechanization kept output tied to human and ecological capacity. Yet these systems accumulated knowledge, institutions, and routes that would later be repurposed. When industrialization began, it did not create supply chains from nothing. It inherited networks shaped by centuries of pre-industrial production. Those inherited forms quietly structured the path forward. By the late pre-industrial era, supply systems had reached a point of structural saturation rather than exhaustion. Production methods, transport limits, and institutional arrangements were finely tuned to existing constraints. Incremental improvements occurred, but they rarely altered underlying dynamics. Tools became marginally more efficient, crop yields improved slowly, and trade routes stabilized through repeated use. The reason transformation remained limited was that energy inputs stayed organic and dispersed. Without concentrated power sources, output could not scale beyond human and animal capacity. According to long-run economic studies, productivity growth before industrialization was minimal over centuries. Gains were often absorbed by population growth rather than surplus expansion. Supply chains therefore maintained balance rather than momentum. They optimized survival within narrow margins. This equilibrium shaped how societies understood production, exchange, and risk. Population growth exerted steady pressure on these systems. As populations expanded, land per capita declined, and marginal productivity fell. The mechanism was cumulative rather than sudden. More labor was applied to the same land with diminishing returns. This worked until subsistence thresholds were reached. According to demographic historians, pre-industrial societies oscillated between growth and correction. Famine, disease, and conflict periodically reduced population levels. Supply systems did not prevent these shocks. They adapted after the fact. Storage, trade, and charity mitigated suffering but rarely eliminated scarcity. These cycles reinforced conservative production choices. Innovation carried risk when margins were thin. As a result, supply chains favored known methods over experimental change. Regional specialization increased gradually but remained constrained. Certain areas became associated with specific outputs, such as wool in England, silk in China, or spices in Southeast Asia. The reason specialization emerged was comparative advantage rooted in climate, skill, or resource availability. This worked when trade routes were reliable enough to exchange surplus. According to historical trade data, such specialization was uneven and reversible. Political instability or environmental change could disrupt regional roles. Producers therefore avoided full dependence on external supply. Mixed production strategies persisted alongside specialization. Supply chains extended but did not harden. Flexibility remained essential for resilience. Commercial intermediaries played a growing role in connecting dispersed producers. Merchants accumulated information about prices, demand, and routes across regions. The mechanism was relational rather than institutional. Trust was built through repeated interaction and reputation. This worked because legal enforcement across borders was weak. According to merchant account records, partnerships were often temporary and adaptive. Capital was mobile, but production was not. Merchants absorbed risk and coordinated exchange without controlling production itself. They stitched together fragmented supply systems without integrating them. Their role expanded connectivity while preserving decentralization. This intermediary function would later become central to industrial supply chains. Technological diffusion remained slow and selective. Innovations such as improved plows, looms, or navigation tools spread unevenly across regions. The reason diffusion was limited was that adoption required local adaptation and acceptance. Techniques that worked in one context often failed in another. According to studies of technological history, resistance to change was rational rather than cultural. New tools required investment and learning without guaranteed returns. Supply chains could not easily absorb failed experiments. As a result, innovation followed conservative pathways. Incremental change accumulated over long periods. Radical shifts remained rare. Political structures influenced supply stability more than expansion. States provided security for trade routes, enforced standards, and extracted surplus. The mechanism was coercive as well as administrative. This worked when authority was stable and predictable. According to historical analyses, periods of strong centralized rule often coincided with expanded trade volumes. However, state collapse could rapidly fragment supply networks. Production systems reverted to local self-sufficiency under threat. This fragility discouraged overextension. Supply chains balanced between opportunity and exposure. Political risk remained embedded in economic structure. Cultural norms shaped consumption patterns and moderated demand. Expectations around quality, variety, and availability were limited by experience. The reason demand remained stable was that novelty was scarce and costly. According to social historians, consumption changed slowly across generations. This reduced pressure on supply systems to diversify or accelerate. Producers responded to customary demand rather than speculative markets. Supply chains therefore aligned with social rhythm rather than growth imperatives. Stability was valued over expansion. This alignment reinforced equilibrium and predictability. As the pre-industrial period drew to a close, its supply systems carried both strength and limitation. They were durable, adaptive, and deeply integrated into social life. They managed risk through redundancy, diversity, and local knowledge. At the same time, they constrained scale, speed, and coordination. These systems formed the inherited landscape upon which industrial production would later operate. When new energy sources and technologies emerged, they encountered existing routes, institutions, and habits. The transformation of supply chains would involve reconfiguring these foundations rather than replacing them entirely. The transition ahead would accelerate movement, concentrate production, and abstract coordination, while still relying on patterns established long before mechanization began. In the centuries before industrialization, supply chains were shaped by proximity, habit, and shared custom. Production and exchange took place within narrow geographic boundaries, often centered on a single town or clustered villages. Goods moved slowly, typically carried by foot, animal, or small cart along unpaved roads. The scale of coordination rarely extended beyond what could be managed through direct observation and personal trust. Markets convened on fixed days, bringing together farmers, artisans, and traders in predictable cycles. These gatherings were not only economic exchanges but also social institutions governed by long-standing expectations. The architecture of supply was visible and tangible, from workshop benches to open market stalls. Craft guilds emerged within this environment as organizing structures that stabilized production and defined the boundaries of trade. By the 12th and 13th centuries, many European towns had formalized associations of artisans into regulated bodies known as guilds. In cities such as Florence, London, and Cologne, these organizations gained legal recognition from municipal authorities. At the time, urban populations were expanding due to agricultural improvements and regional trade growth. Guilds defined who could produce specific goods, how they would be made, and where they could be sold. Membership was typically restricted to trained masters who had completed apprenticeships and produced approved work. By 1300, entire districts within major towns were associated with particular crafts, from weaving to metalwork. The structure limited competition but ensured consistent standards within local markets. Historical records show that guild charters often included detailed rules about pricing, materials, and quality inspection. The mechanism that sustained guild control rested on layered apprenticeship systems. Young apprentices entered workshops for years of supervised training under master craftsmen. The reason this structure endured was that skill transmission required proximity and repetition rather than written instruction. This works because complex techniques were embedded in habit and muscle memory, reinforced through daily practice. After apprenticeship, individuals progressed to journeyman status, working for wages while refining their craft. Only after producing a masterwork that met guild approval could they open independent workshops. The sequence created predictable career paths and stabilized the supply of skilled labor. It also regulated output, since the number of masters directly influenced total production capacity. In effect, guilds aligned labor supply with local demand through institutional control rather than market competition. Local markets operated within equally structured boundaries shaped by geography and custom. Rural producers brought grain, livestock, and raw materials into towns at designated intervals. Artisans converted these inputs into finished goods that circulated within the same region. Transport costs imposed natural limits on how far products could travel before becoming uncompetitive. As a result, supply chains were short, often consisting of 2 or 3 distinct stages. The relationships between participants were repeated and personal, reinforced by reputation and community oversight. Disputes over quality or payment were handled through local courts or guild mediation. The visibility of each stage reduced uncertainty and allowed communities to monitor economic behavior closely. According to municipal archives from medieval trading centers, price fluctuations were relatively modest compared to later industrial periods. Studies show that seasonal cycles influenced supply more than distant events or external shocks. The reason for this stability was limited integration with faraway markets. This works because isolated systems dampen the transmission of volatility across regions. When harvests failed locally, scarcity emerged, but abundance elsewhere did not immediately offset shortages. Information traveled slowly, carried by messengers or itinerant merchants rather than standardized reports. The absence of rapid communication preserved regional autonomy but constrained growth. Economic coordination was therefore bounded by the speed of travel and the reach of personal networks. At the same time, certain towns became specialized hubs within broader regional webs. By the 14th century, textile centers in Bruges and metalworking districts in Nuremberg had developed reputations that extended beyond local borders. At the time, merchants began linking these centers through periodic fairs that connected multiple markets. Caravans and river barges carried standardized goods between towns during these events. Although still limited in scale, these exchanges introduced elements of interdependence. Guild regulations often adapted to accommodate external demand while preserving local authority. By 1400, some guilds negotiated collectively with merchant groups to coordinate volumes and delivery schedules. These arrangements foreshadowed more complex supply coordination that would later define international trade. The mechanism underlying these expanding networks involved incremental trust building between distant actors. The reason merchants risked transporting goods across regions was the expectation of enforceable contracts at destination markets. This works because reputational systems extended beyond single towns through shared legal traditions and merchant associations. Written agreements gradually supplemented oral commitments, reducing ambiguity in transactions. Credit instruments began to circulate, allowing payments to be deferred without halting trade flows. The introduction of standardized weights and measures further reduced friction between markets. Each incremental improvement lowered transaction costs while maintaining guild oversight at the production stage. Supply chains lengthened cautiously, balancing opportunity against uncertainty. Despite these developments, most economic life remained grounded in locality. Workshops produced in small batches, calibrated to predictable patterns of demand. Market days structured the rhythm of exchange, tying supply to communal calendars. Guild halls stood as visible centers of authority, reinforcing collective standards and shared identity. The boundaries of trade were understood intuitively, shaped by terrain, language, and jurisdiction. Yet the growing coordination between towns suggested latent potential for wider integration. Gradual adjustments in transport, finance, and governance were quietly extending the reach of production networks. Within these evolving patterns, the foundations of more expansive supply systems were already forming. As towns expanded in population and commercial ambition, the internal organization of guild production grew more intricate. Workshops that once served only neighborhood demand began calibrating output to serve surrounding villages and satellite settlements. This gradual widening of market radius required tighter coordination of materials, labor, and delivery timing. Masters kept detailed mental records of recurring orders and seasonal fluctuations in demand. The predictability of these cycles allowed production to be planned months in advance without written forecasting tools. Journeymen traveled between towns carrying both skills and information about prevailing prices. Such movement subtly linked once isolated markets into overlapping economic zones. The supply chain remained short in physical distance, yet it began to stretch conceptually as awareness of external demand increased. This quiet broadening marked a shift from purely local provisioning toward regionally responsive production. The mechanism that enabled this expansion rested on structured procurement of raw materials. Artisans depended on reliable access to inputs such as wool, timber, ore, and dyes. The reason procurement became more organized was the need to avoid interruptions that could damage reputation. This works because customers valued consistency as much as craftsmanship. Guilds often negotiated collectively with rural suppliers to secure steady deliveries at agreed prices. Storage facilities were constructed to hold reserves against poor harvests or delayed transport. These buffers reduced vulnerability to seasonal shocks while preserving workshop continuity. Transporters developed regular routes linking farms, forests, and mines to urban centers. Over time, procurement networks displayed patterns that resembled early forms of logistical planning. By the late 14th century, regional fairs had become predictable nodes within broader exchange circuits. At the time, merchants from multiple territories converged on designated towns during fixed calendar periods. In places such as Geneva and Frankfurt, these gatherings facilitated bulk transactions beyond ordinary market scale. Guild representatives attended not merely to sell finished goods but to observe trends in demand and pricing. Written records from this period indicate increasing attention to comparative advantage between towns. By 1450, some guilds had begun specializing more narrowly to differentiate their output from neighboring producers. This specialization subtly lengthened supply chains by increasing interdependence among regions. Goods might pass through several hands before reaching final consumers. Information flow became a critical component of these emerging networks. According to surviving correspondence between merchants and guild masters, news of shortages or surpluses traveled alongside caravans. Studies show that price signals moved faster along established trade corridors than through isolated rural districts. The reason was the density of relationships among recurring participants. This works because trust reduced the need for repeated verification of information. Couriers and letter carriers gradually formed semi-professional services linking major towns. The presence of shared commercial languages further streamlined communication across linguistic boundaries. Reliable information lowered uncertainty and encouraged calculated risk-taking in larger transactions. Communication infrastructure, therefore, became an invisible but essential layer within the supply chain. Credit arrangements expanded in parallel with these informational improvements. Artisans who once demanded immediate payment increasingly accepted deferred settlement through trusted intermediaries. The mechanism involved promissory notes and rudimentary banking partnerships operating within urban centers. The reason such instruments spread was the limitation of coin supply relative to trade volume. This works because written commitments could circulate as substitutes for physical currency. Guild oversight remained strong, ensuring that members honored obligations to preserve collective credibility. Default carried social consequences that extended beyond individual workshops. The extension of credit effectively stretched supply chains across time as well as space. Production could proceed before final payment was received, allowing greater output than cash alone would permit. Urban authorities played a stabilizing role in this transformation. Municipal councils granted charters that clarified commercial rights and responsibilities. At the time, civic courts enforced contracts and mediated disputes between guilds and merchants. Cities such as Venice developed reputations for predictable legal procedures that attracted external traders. By 1500, standardized documentation practices were common in many trading centers. These legal frameworks reduced transaction costs by providing recourse in cases of breach. The existence of credible enforcement encouraged participants to engage in more distant and complex exchanges. Governance structures thus formed another pillar supporting the gradual elongation of supply networks. Despite these advances, production techniques remained constrained by manual processes. Workshops relied on human and animal power rather than mechanized systems. Output increases, therefore, depended primarily on the number of skilled workers available. The mechanism linking labor supply to output remained direct and visible. The reason scale was limited was the time required to train competent artisans. This works because expertise could not be rapidly replicated without diluting quality. Guild quotas sometimes restricted the number of masters permitted within a town. Such limits preserved income stability but slowed expansion into wider markets. Growth proceeded incrementally, balanced between opportunity and preservation of standards. The cumulative effect of these adjustments was a supply structure that balanced local rootedness with emerging regional connectivity. Markets were no longer isolated circles but overlapping layers connected through fairs, credit, and shared regulation. Production still began in small workshops where tools and materials were arranged within arm's reach. Yet the destination of finished goods increasingly lay beyond immediate neighborhoods. Coordination required foresight, record-keeping, and negotiated agreements that extended across jurisdictions. Economic life was becoming more interlinked without losing its craft foundations. The pattern suggested capacity for further integration as transport and finance evolved. Within these slowly lengthening chains, the outlines of a broader commercial system were taking shape. Over time, the limits of purely local organization became increasingly visible within expanding European economies. Population growth placed sustained pressure on food supply, raw materials, and manufactured goods. Towns that once functioned as largely self-contained systems began to rely more consistently on surrounding regions. Artisans noticed that demand could outpace the capacity of established workshops during periods of prosperity. Seasonal fairs no longer absorbed the full volume of exchange that merchants sought to conduct. Gradual urban expansion altered consumption patterns, increasing appetite for specialized and higher quality goods. These changes did not dismantle guild structures, but they exposed structural constraints embedded within them. Production remained carefully regulated, yet external forces were beginning to test those boundaries. The supply chain was still grounded in local relationships, but its edges were under quiet strain. The mechanism of constraint centered on restricted entry and controlled output. Guild statutes often limited the number of masters permitted to operate within city walls. The reason for these limits was income protection and quality assurance. This works because fewer producers could maintain higher margins and consistent oversight. However, fixed membership reduced the system's flexibility when external demand rose unexpectedly. Merchants seeking larger volumes sometimes turned to rural producers operating outside strict guild supervision. Informal networks emerged in the countryside where regulation was lighter and costs were lower. These parallel channels created tension between urban authorities and peripheral workshops. Control over the supply chain was therefore no longer absolute, even if guilds retained formal authority. By the 16th century, certain regions displayed early forms of proto-industrial organization. At the time, textile merchants in areas surrounding Antwerp coordinated spinning and weaving across dispersed rural households. Rather than concentrating all labor within a single workshop, they distributed raw materials to families who worked from their homes. By 1550, similar arrangements could be observed in parts of Leiden and northern Italy. Written contracts specified quantities and delivery dates, even though production remained manual. This diffusion of labor expanded output beyond what guild-capped urban shops could achieve. Goods flowed back into towns for finishing, inspection, and sale. The chain linking fiber to finished cloth now stretched across multiple settlements. According to economic historians examining tax records from this period, output in certain sectors rose without proportional increases in urban workshop numbers. Studies show that decentralized production reduced overhead while maintaining acceptable quality standards. The reason was that merchants assumed coordination roles previously held by guild masters. This works because centralized control of materials and credit allowed dispersed labor to operate in synchrony. Risk shifted gradually from individual artisans to merchant organizers who financed production cycles. Information about market demand became more critical as distances between stages increased. Delays or miscalculations could now disrupt several linked households rather than a single shop. The supply chain was evolving into a layered structure with distinct managerial functions. Transportation improvements reinforced these structural adjustments. Investment in road maintenance, river navigation, and port facilities reduced transit time between regions. The mechanism was straightforward, as lower friction in movement expanded feasible trade radii. The reason such infrastructure mattered was the cumulative effect on cost and reliability. This works because predictable delivery schedules enabled more complex contractual arrangements. Carriers developed regular routes connecting inland towns to maritime outlets. Warehouses near docks began to store goods awaiting shipment to distant markets. These logistical nodes introduced temporal buffering into the chain, separating production from immediate sale. Physical space dedicated to storage signaled a subtle shift toward anticipatory distribution rather than reactive exchange. Financial practices adapted in parallel with logistical expansion. Bills of exchange circulated more widely, linking merchants across cities and kingdoms. At the time, banking families in centers such as Augsburg and Genoa facilitated cross-regional settlements. By 1600, commercial credit networks extended across much of Western Europe. These instruments reduced the need to transport large quantities of coin alongside merchandise. The separation of payment from physical goods decreased risk and increased transaction speed. Merchant capital could be redeployed into successive production cycles without waiting for metal currency to return. Financial abstraction therefore lengthened supply chains while binding participants through contractual obligation. Despite widening horizons, guild identity remained influential within urban life. Ceremonies, apprenticeship rituals, and collective decision-making reinforced internal cohesion. Workshops continued to emphasize craftsmanship and reputation as primary assets. Yet, economic gravity was shifting toward actors who coordinated multiple stages rather than mastering a single craft. The mechanism of change lay in comparative advantage between production skill and organizational capacity. The reason merchants gained influence was their control over capital and information flows. This works because integrated oversight across regions generated efficiencies unavailable to isolated shops. Guilds adapted unevenly, sometimes cooperating with merchants and sometimes resisting encroachment. Tension between tradition and expansion became a defining feature of late pre-industrial supply systems. By the early 17th century, the outlines of a more expansive commercial architecture were visible across Europe. Production was no longer confined to tightly bounded urban districts, even if guild halls still stood at their center. Raw materials traveled farther before transformation, and finished goods circulated across wider territories. Credit, contracts, and infrastructure quietly connected households, workshops, warehouses, and ports. Local markets persisted, but they operated within increasingly interdependent regional frameworks. Authority was distributed among guilds, merchants, financiers, and civic officials. The supply chain had evolved from a short sequence of face-to-face exchanges into a coordinated web spanning multiple jurisdictions. These cumulative adaptations prepared the ground for the more dramatic reorganizations that would accompany industrialization. The transition from localized production to industrial-scale manufacturing marked a structural transformation in global supply chains. Workshops that once relied on small teams of artisans gradually gave way to centralized factories organized around machinery and standardized processes. Production no longer revolved around individual skill alone, but around coordinated systems designed for repetition and volume. This shift required significant capital investment in buildings, engines, and mechanical tools. It also required new forms of labor organization capable of sustaining continuous output. The factory became not only a place of work, but a node in a widening network of suppliers and distributors. Raw materials traveled greater distances to reach centralized plants. Finished goods moved outward in growing quantities toward regional and international markets. The supply chain began to stretch geographically while becoming more tightly controlled internally. Industrial-scale manufacturing introduced a rhythm defined by machines, schedules, and measurable output. That rhythm would reshape the movement of goods across continents. By the late 18th century, mechanization had begun altering production in sectors such as textiles and metalworking. In 1764, the spinning jenny increased yarn output dramatically within a single workshop. By 1785, steam engines refined by James Watt powered machinery independent of water sources. At the time, Britain possessed access to coal deposits that enabled sustained mechanical energy. By 1800, textile mills clustered in regions where transportation links connected ports and inland towns. Railways expanded rapidly after the 1830s, reducing transit time for both raw cotton and finished cloth. According to economic historians, industrial output in Britain multiplied several times within a few decades. Similar patterns later emerged in parts of continental Europe and North America. The concentration of machinery, labor, and energy in single facilities marked the beginning of industrial-scale manufacturing as a dominant model. These developments laid the foundation for supply chains that depended on predictable, high-volume production. The mechanism of industrial-scale manufacturing depended on dividing complex tasks into standardized steps. Each worker performed a limited function within a coordinated sequence, reducing variability in output. This works because repetition increases speed while lowering the likelihood of error in a controlled environment. Machinery amplified this effect by maintaining consistent motion and force. Interchangeable parts further simplified assembly, allowing components produced in different locations to fit together without modification. The reason this mattered for supply chains was predictability. When output became consistent, downstream distributors could plan inventory and transport with greater accuracy. Bulk purchasing of inputs reduced per-unit costs and strengthened bargaining power with suppliers. Economies of scale emerged as fixed costs were spread across larger production volumes. The factory system therefore linked internal efficiency with external coordination. Industrial-scale manufacturing turned production into a calculable process embedded within expanding networks of exchange. As factories expanded, they required stable inflows of raw materials sourced from distant regions. Cotton traveled from plantations in the American South and India to mills in Britain. Iron ore and coal moved from mining districts to steelworks and foundries. Timber, rubber, and other commodities entered industrial centers through ports connected to colonial trade routes. The scale of these movements demanded improved infrastructure. Canals, railways, and steamships reduced transportation costs and synchronized supply with factory schedules. Warehouses emerged near industrial hubs to buffer fluctuations in delivery times. Insurance markets developed to manage the financial risk of long-distance shipment. According to trade records from the 19th century, the volume of maritime cargo increased steadily alongside industrial output. Supply chains became multi-layered systems in which extraction, processing, manufacturing, and distribution were spatially separated but economically interdependent. The geography of production widened while coordination tightened. Industrial-scale manufacturing also transformed labor relations and organizational hierarchy. Factory owners implemented time discipline to ensure machines operated continuously. Work shifts replaced seasonal rhythms that had characterized agricultural and artisanal life. Supervisors monitored output and enforced standardized procedures. The reason for this oversight was efficiency rather than tradition. This works because synchronized labor maximizes machine utilization and minimizes idle capacity. Wage labor expanded as individuals sold time rather than completed goods. Urban populations grew as workers migrated toward industrial centers seeking employment. By the mid-19th century, cities such as Manchester and Pittsburgh had become industrial hubs defined by dense factory districts. According to demographic studies, urban growth correlated closely with manufacturing expansion during this period. The internal organization of factories mirrored the broader structure of supply chains, with layered management overseeing flows of materials and labor. Industrial-scale manufacturing reshaped both economic geography and social structure. Technological innovation continued to refine industrial production throughout the 19th and early 20th centuries. The introduction of the Bessemer process in 1856 reduced the cost of steel production significantly. By 1913, assembly line techniques implemented in automobile factories accelerated output to unprecedented levels. At the time, standardized components allowed vehicles to be assembled rapidly by semi-skilled workers. Electrification replaced steam in many facilities, enabling flexible plant layouts and extended operating hours. According to production statistics from the early 20th century, manufacturing output in the United States surpassed that of many European nations combined. These gains were not isolated events but part of an ongoing trajectory toward greater scale and coordination. Rail and maritime networks expanded in parallel, ensuring that increased production could reach distant consumers. Industrial-scale manufacturing matured into a global system supported by technological integration and logistical planning. The mechanism linking industrial production to global supply chains relied on synchronization across multiple stages. Raw material extraction had to align with factory capacity to avoid shortages or surpluses. Transportation schedules needed to match production cycles so that finished goods did not accumulate excessively. The reason this coordination was essential lies in capital intensity. Large factories required continuous throughput to justify investment in machinery and infrastructure. This works because steady flow reduces downtime and stabilizes revenue streams. Financial institutions played a supporting role by extending credit to manage cash flow between production and sale. Accounting systems evolved to track inventory, depreciation, and operating costs with precision. According to business archives from the early 20th century, firms that mastered logistical coordination achieved more stable profit margins. Industrial-scale manufacturing, therefore, depended on information as much as machinery. Supply chains became integrated systems governed by data, timing, and contractual relationships. As the 20th century progressed, industrial-scale manufacturing extended beyond Europe and North America into Asia and other regions. Multinational corporations established facilities near sources of labor and raw materials to reduce costs. Ports expanded to accommodate larger steamships and later motorized vessels capable of carrying bulk cargo. Governments invested in highways and rail corridors to connect industrial zones with export terminals. According to trade data compiled after the Second World War, global merchandise flows increased steadily alongside manufacturing output. The structure of supply chains grew more complex as components crossed borders multiple times before final assembly. Industrial-scale manufacturing created interdependence between distant economies. Production decisions in one country influenced employment and resource extraction in another. The system continued to expand in scope and sophistication, setting the stage for the logistical revolutions that would define the late 20th century. Industrial-scale manufacturing did not merely increase output, it altered the logic of coordination across entire regions. Factories required steady inflows of standardized inputs delivered at predictable intervals. This requirement encouraged long-term contracts between producers and suppliers. Agricultural producers adjusted crop patterns to meet industrial demand for cotton, flax, and other fibers. Mining operations expanded in response to rising consumption of coal and iron ore. Transportation companies synchronized timetables with factory production cycles. Warehousing evolved from simple storage to an active buffer against uncertainty. The growing complexity of these arrangements required formal management structures capable of oversight and planning. Written contracts replaced informal agreements in many sectors. Insurance instruments spread risk across broader pools of investors. The supply chain increasingly resembled a managed system rather than a series of isolated transactions. Industrial-scale manufacturing anchored this transformation through its constant demand for volume and reliability. The internal architecture of factories reinforced this outward expansion. Production floors were organized around linear flows of materials moving from one station to the next. This works because sequential arrangement minimizes unnecessary handling and delay. Supervisors tracked throughput at each stage to identify bottlenecks. Mechanical power sources were positioned to distribute energy efficiently across multiple machines. Standard operating procedures reduced reliance on individual discretion. The reason for such precision was financial exposure. Large capital investments in equipment demanded consistent utilization to remain profitable. Idle machines represented sunk costs without return. Timekeeping systems recorded hours with increasing accuracy. Payroll departments emerged to manage growing workforces. The disciplined interior of the factory mirrored the disciplined exterior of supply chains. Coordination became both a technical and administrative achievement sustained by routine measurement. By the mid-19th century, telegraph networks introduced faster communication between industrial centers and ports. Messages that once required days of travel could be transmitted in minutes. At the time, commodity prices fluctuated in response to harvests, strikes, and geopolitical events. Merchants used telegraphic information to adjust purchasing decisions rapidly. Rail companies relied on signals and schedules coordinated across expanding track networks. According to business correspondence from the period, managers increasingly depended on remote updates to guide shipment timing. The integration of communication technology reduced uncertainty in long-distance trade. Financial markets responded more quickly to news affecting production. Insurance rates adjusted in response to reported risks along trade routes. Industrial-scale manufacturing benefited from this acceleration because supply chains could react with greater agility. Information began to move faster than physical goods, shaping decisions before materials arrived. Mass production techniques intensified during the late 19th century as firms pursued uniformity at scale. Standard gauges for railways enabled rolling stock to travel across national borders without modification. Interchangeable mechanical components simplified repair and maintenance across distant markets. This works because uniform standards reduce friction between independent actors. The reason standardization expanded globally was competitive pressure. Firms that adopted common specifications could source inputs from multiple suppliers. Governments often supported harmonized measurements to facilitate trade. According to industrial surveys from the early 20th century, sectors with high degrees of standardization achieved lower per-unit costs. The predictability of parts encouraged the growth of secondary industries focused on maintenance and distribution. Industrial-scale manufacturing thus fostered ecosystems of related enterprises. Supply chains extended outward in layered formations built on shared technical norms. Labor specialization deepened as output volumes climbed. Workers trained for narrowly defined tasks, sometimes repeating the same motion thousands of times per shift. This works because repetition increases speed and reduces variability. The reason firms favored such specialization lay in productivity metrics. Measurable output per worker allowed managers to calculate efficiency precisely. Training periods shortened because tasks required limited conceptual understanding. However, dependence on specialized labor also introduced vulnerability to disruption. Strikes or shortages in key roles could halt entire production lines. According to labor records from industrial cities, work stoppages often reverberated across supplier networks. Employers responded by diversifying sourcing and investing in managerial oversight. Industrial-scale manufacturing therefore balanced efficiency gains with exposure to coordinated interruption. Supply chains absorbed these lessons by building redundancy where feasible. The rise of vertically integrated firms represented another adaptation to industrial-scale demands. Companies acquired or established control over raw material extraction, processing, and distribution channels. This works because internal ownership reduces transaction costs and uncertainty. The reason integration appealed to industrial leaders was stability. Controlling multiple stages insulated production from price swings and supplier failure. Large enterprises developed internal transportation fleets and private storage facilities. Accounting departments tracked costs across divisions to assess performance. According to corporate reports from the early 20th century, integrated firms often achieved greater profit consistency. However, integration also required substantial capital and managerial sophistication. Industrial-scale manufacturing provided the volume necessary to justify such investments. Supply chains became partially internalized within corporate boundaries while still connected to external markets. Global trade patterns shifted as industrial powers sought secure access to raw materials. Colonial administrations invested in rail lines and ports designed primarily for export. At the time, manufactured goods flowed outward while primary commodities flowed inward. Tariff policies influenced sourcing decisions and shaped regional specialization. According to trade statistics compiled before the First World War, industrial nations accounted for a disproportionate share of manufactured exports. Shipping companies expanded fleets to accommodate steady cargo volumes. Financial institutions in major cities financed overseas infrastructure tied to extraction and transport. Industrial-scale manufacturing depended on these external networks to sustain throughput. The geography of supply chains reflected political and economic hierarchies embedded in global systems. Production centers and resource peripheries became linked through structured flows of capital and goods. As industrial-scale manufacturing matured, attention turned toward efficiency in inventory management. Firms recognized that excessive stock tied up capital without generating immediate return. This works because stored goods represent deferred revenue and storage cost. The reason managers focused on inventory lay in competitive pressure to reduce waste. Statistical methods emerged to forecast demand more accurately. Warehouses adopted systematic cataloging to track quantities and turnover rates. According to early management literature, firms that aligned production closely with sales reduced financial volatility. Transportation schedules were adjusted to deliver inputs closer to the moment of use. These refinements foreshadowed later logistical innovations that would compress timelines further. Industrial-scale manufacturing continued to evolve toward tighter synchronization across stages. Supply chains increasingly prioritized flow over accumulation as coordination advanced. By the early 20th century, industrial-scale manufacturing had become the dominant mode of production in many advanced economies. Large factories operated with thousands of workers coordinated through layered management hierarchies. Production targets were set months in advance and tied to sales projections across national markets. This environment required systematic forecasting rather than reactive adjustment. firms began gathering statistical data on consumer demand, seasonal variation, and regional purchasing patterns. The reason for this expansion of record-keeping was stability. Predictable demand reduced the risk of overproduction and sudden contraction. Managers relied on ledgers and later mechanical tabulators to process growing volumes of information. According to corporate archives from the interwar period, planning departments expanded significantly in size and authority. Industrial-scale manufacturing thus fused physical production with administrative calculation. Supply chains increasingly depended on forward planning anchored in quantitative analysis. The mechanism of large-scale coordination relied on aligning procurement, production, and distribution in a continuous loop. Raw materials were ordered based on projected output rather than immediate necessity. This works because synchronized planning reduces emergency purchases at unfavorable prices. Production schedules were adjusted to match anticipated shipment windows. Railways and shipping lines operated on fixed timetables that factories incorporated into internal calendars. The reason timing became central was capital intensity. Machinery required constant operation to amortize its cost over sufficient units. Downtime translated directly into financial loss. Accounting systems evolved to measure turnover ratios and throughput velocity. According to early management theorists, efficiency could be quantified through time and motion studies. Industrial-scale manufacturing therefore transformed supply chains into temporal systems governed by clocks and ledgers. Technological standardization reached new heights during the first half of the 20th century. Electrical grids unified power supply across regions, allowing factories to operate with consistent voltage and frequency. By the 1920s, telephone networks connected managers to suppliers in near real time. At the time, global shipping routes linked continents through regular steamship service. The Panama Canal, completed in 1914, shortened transit between Atlantic and Pacific markets. According to trade records from the period, intercontinental cargo volumes expanded steadily despite geopolitical instability. These infrastructural milestones reinforced the reliability of long-distance exchange. Industrial-scale manufacturing could now depend on predictable maritime corridors and communication lines. The integration of energy, transport, and communication systems deepened the reach of supply chains. Production decisions in one region reverberated rapidly across oceans. The Great Depression exposed the fragility of industrial-scale coordination under conditions of collapsing demand. Factories designed for continuous output faced sudden contraction in orders. This works because fixed costs remain even when revenue declines. The reason the crisis spread quickly was interdependence. Reduced purchasing in one sector diminished orders for upstream suppliers. Financial strain limited access to credit necessary for inventory and payroll. According to economic studies of the 1930s, industrial output in many countries declined by double-digit percentages. Governments responded with public works programs and regulatory reforms aimed at stabilizing markets. New labor protections altered the balance between employers and workers. Industrial-scale manufacturing survived but required stronger institutional frameworks. Supply chains became more closely linked to state policy and macroeconomic management. The Second World War accelerated industrial integration on an unprecedented scale. Governments coordinated production across private firms to meet military demand. At the time, factories shifted from consumer goods to armaments, vehicles, and equipment. Central planning agencies allocated raw materials according to strategic priority. According to wartime production reports, output of ships, aircraft, and vehicles increased several-fold within a few years. Standardization intensified to ensure interchangeability across units produced in different plants. Logistics networks expanded to move supplies across continents and oceans. The mechanism of coordination relied on centralized data collection and strict scheduling. Industrial-scale manufacturing demonstrated its capacity for rapid expansion under unified direction. Supply chains operated as national systems mobilized toward collective objectives. After 1945, industrial economies transitioned from wartime mobilization to peacetime consumption. Mass production techniques refined during conflict were redirected toward automobiles, appliances, and consumer goods. This works because high-volume output lowers unit cost when demand is broad and stable. The reason post-war growth proved durable lay in rising household income and expanding credit markets. Suburbanization increased demand for manufactured products tied to housing and transportation. According to economic statistics from the 1950s and 1960s, manufacturing employment and output grew steadily across several regions. International institutions promoted trade liberalization, reducing barriers between markets. Shipping technology improved with larger vessels and more efficient cargo handling methods. Industrial-scale manufacturing became embedded in a progressively interconnected global economy. Supply chains extended across borders with increasing regularity and volume. Managerial innovation accompanied this expansion in scope. Firms adopted formal strategic planning frameworks to evaluate long-term investment decisions. The mechanism of corporate governance separated ownership from daily management in many large enterprises. This works because specialized managers can focus on operational efficiency while shareholders provide capital. The reason such separation expanded was scale. Complex supply chains required professional oversight beyond the capacity of individual proprietors. Universities developed business administration programs to train managers in accounting, logistics, and organizational theory. According to surveys conducted in the mid-20th century, firms that implemented structured planning often achieved more stable growth trajectories. Information systems gradually incorporated electronic data processing, reducing clerical error. Industrial-scale manufacturing thus merged physical infrastructure with managerial science. Supply chains became arenas for systematic optimization guided by formal analysis. By the late 20th century, the cumulative effects of industrial-scale manufacturing had reshaped the global economic landscape. Production networks spanned continents, linking extraction sites, processing plants, assembly facilities, and consumer markets. This works because advances in transportation and communication compressed distance. The reason complexity continued to increase lay in specialization. Firms concentrated on core competencies while outsourcing complementary functions. Trade agreements facilitated cross-border investment and component sourcing. According to international trade data from the final decades of the century, intermediate goods accounted for a growing share of global commerce. Industrial-scale manufacturing evolved into distributed systems of coordinated production rather than isolated national industries. Supply chains operated with heightened efficiency yet remained exposed to disruption. The foundations established during the industrial era prepared the ground for a new phase of logistical transformation centered on speed, precision, and digital integration. By the early 19th century, industrial production had expanded beyond the confines of local markets, creating a growing dependence on reliable movement between distant regions. Factories could produce at unprecedented scale, but scale alone was insufficient without transport systems capable of distributing output efficiently. Railways, canals, and steamships emerged not as isolated inventions, but as integrated components of a broader logistical transformation. At the time, manufacturers began to think in terms of networks rather than individual transactions. Goods no longer moved only when buyers appeared at the factory gate. Instead, production schedules increasingly aligned with shipping timetables and warehouse capacities. This alignment marked a subtle but decisive shift in economic organization. Transportation ceased to be a peripheral service and became a structural foundation of supply chain architecture. The mechanism that links transportation to supply chain expansion rests on cost, speed, and predictability. The reason these variables matter is that distance imposes friction on exchange. When transport becomes cheaper and more reliable, markets effectively expand without physical relocation of production sites. This works because lower friction reduces the uncertainty embedded in every transaction. Producers can commit to larger output volumes when they trust that distribution channels will absorb goods consistently. Retailers can diversify inventory when replenishment cycles become predictable. Financial institutions extend credit more confidently when shipment times stabilize. Over time, this reduction in uncertainty encourages specialization across regions. Transportation therefore acts not merely as a conduit for goods, but as an enabler of coordinated economic behavior across space. Steam power intensified these dynamics throughout the 19th century. By 1850, railway mileage in the United States had surpassed 9,000 miles, linking agricultural interiors with coastal ports. In Britain, dense rail networks connected manufacturing centers such as Manchester and Birmingham to London and Liverpool. At the time, steamships shortened transatlantic crossings from weeks to predictable schedules measured in days. According to shipping records from the period, freight costs per ton declined steadily as vessel size increased. These developments allowed perishable goods to travel farther without spoilage. They also enabled raw materials such as cotton, coal, and iron to circulate between continents with greater regularity. By the late 19th century, global trade volumes had multiplied several times over compared to pre-industrial levels. As transportation capacity expanded, coordination became the next critical frontier. Moving goods quickly was valuable, but synchronizing movement across multiple stages of production proved equally important. Warehouses evolved from simple storage spaces into strategic buffers between production and distribution. Telegraph networks allowed shipping agents to communicate arrival times and adjust routing decisions in near real time. The reason coordination systems developed alongside transport infrastructure is that complexity increases with scale. A single delayed shipment could halt an entire production line dependent on sequential inputs. Businesses therefore invested in administrative systems to track inventory, schedule deliveries, and manage documentation. These early coordination mechanisms laid the groundwork for modern logistics management. They represented an institutional response to the opportunities created by faster movement. The mechanism of coordination operates through information flow. Physical transport moves goods, but information synchronizes actions across participants. This works because supply chains consist of interdependent nodes that must align in timing and quantity. When information lags behind physical movement, inefficiencies multiply. Overstocking, stockouts, and idle labor emerge as symptoms of misalignment. Studies of early 20th century rail distribution systems show that standardized timetables reduced idle railcar times significantly. According to economic historians, firms that adopted centralized scheduling departments achieved measurable cost savings compared to decentralized competitors. The reason is straightforward. Predictable information reduces the need for excessive safety margins. Over time, this informational discipline allowed firms to compress delivery windows and operate with leaner inventories. By the early 20th century, motorized trucking began to complement rail systems, especially for shorter distances. At the time, paved road networks expanded gradually across Europe and North America. Trucks introduced flexibility that fixed rail lines could not provide. They connected factories directly to urban retail centers and rural suppliers without requiring transshipment at rail depots. According to transportation data from the 1920s, the share of goods moved by road increased steadily in industrialized economies. This diversification of transport modes created layered networks rather than singular corridors. Businesses could select routes based on cost, urgency, and destination constraints. The supply chain became multimodal, blending rail, road, and maritime links into coordinated systems. Containerization later transformed these systems by standardizing the physical unit of transport. The mechanism behind container efficiency lies in interoperability. When goods are packed into uniform steel containers, they can shift seamlessly between ships, trucks, and trains without repacking. This works because standardized dimensions eliminate handling variability at transfer points. By the 1970s, major ports had invested heavily in cranes and terminal layouts optimized for container throughput. According to international trade statistics, container shipping reduced loading times from days to hours in many ports. Labor costs declined, theft decreased, and damage rates fell substantially. As reliability improved, firms reorganized production geographically, confident that distant suppliers could deliver components on strict schedules. Transportation and coordination had merged into a single integrated logic. Over time, the combined evolution of transport infrastructure and coordination systems reshaped the geography of production. Regions specialized according to comparative advantages, trusting that networks would bridge physical separation. Ports expanded into vast logistical complexes, linked by highways and rail corridors to inland distribution hubs. Information technologies layered digital oversight onto physical movement, refining synchronization further. The reason global supply chains achieved such scale lies in this dual foundation. Movement without coordination produces chaos, and coordination without movement produces stagnation. Together, they create a system capable of spanning continents with measured precision. The architecture of global exchange now rests on synchronized motion, sustained by infrastructure that continues to evolve. As transportation networks matured, firms began reorganizing production around the assumption of continuous flow. Factories no longer operated as isolated centers of output, but as nodes embedded within larger logistical systems. The expansion of highways, rail corridors, and deepwater ports reinforced the expectation that materials would arrive on schedule. This expectation gradually altered managerial decision-making. Production planning incorporated transit times as fixed variables rather than uncertain estimates. Warehousing shifted from long-term storage toward rapid turnover facilities designed for throughput. The supply chain increasingly resembled a moving stream rather than a static inventory pool. Coordination mechanisms evolved in response to this structural shift. The mechanism underlying continuous flow depends on synchronization across multiple actors. Suppliers, carriers, distributors, and retailers must align their schedules with precision. The reason this alignment matters is that delays propagate quickly through interconnected systems. A late shipment of components can idle machinery and labor simultaneously. This works because modern production often relies on sequential assembly processes. Each stage depends on the timely completion of the previous one. As firms reduced buffer inventories to cut costs, tolerance for disruption declined. Coordination systems therefore emphasized forecasting, scheduling, and contingency planning. Over time, predictability became as valuable as speed. By the mid-20th century, advances in aviation introduced a new dimension to transportation. Air freight remained expensive compared to maritime shipping, but it offered unmatched speed for high-value goods. At the time, electronics manufacturers and pharmaceutical companies began using air transport to meet tight delivery requirements. According to trade data from the 1960s, the volume of air cargo grew steadily despite higher per-unit costs. The reason was strategic rather than purely economic. Rapid delivery reduced the need for extensive warehousing and enabled faster market responsiveness. Perishable products and time-sensitive components benefited most from this capability. Air transport thus integrated into supply chains not as a replacement for slower modes, but as a complementary option. Coordination technologies advanced alongside these new transport options. Early computer systems introduced in the 1950s allowed firms to digitize inventory records and automate basic scheduling tasks. The mechanism here rested on centralized data processing. Information that once required manual reconciliation across paper ledgers could now be aggregated electronically. This works because digital records reduce transcription errors and accelerate calculation. According to management studies from the 1970s, firms that adopted computerized inventory control systems reported lower stock discrepancies. These systems enabled more accurate demand forecasting and reorder timing. Over time, digital coordination reduced the administrative burden associated with complex distribution networks. The integration of computing power marked a transition toward data-driven logistics management. The emergence of standardized shipping documentation further streamlined global exchange. Bills of lading, customs declarations, and insurance forms gradually became harmonized across jurisdictions. The reason standardization matters lies in transaction efficiency. When documentation requirements vary widely, processing delays accumulate at border crossings. This works because each deviation requires manual review and clarification. International agreements sought to reduce these frictions by defining common formats and procedures. According to trade policy analyses, countries that simplified customs protocols experienced measurable increases in trade throughput. Administrative predictability reinforced physical infrastructure improvements. The supply chain increasingly depended on regulatory coordination as much as mechanical capability. As global trade intensified in the late 20th century, corporations expanded supplier networks across continents. Components for a single product could originate in multiple countries before final assembly. At the time, improvements in telecommunications allowed managers to monitor operations remotely. Satellite communications and later internet connectivity shortened response times to emerging disruptions. The mechanism of global coordination relied on real-time visibility. Firms tracked shipments through barcode systems and electronic data interchange platforms. According to logistics research, improved tracking reduced lost shipments and enhanced delivery reliability. The supply chain became not only faster, but more transparent. Transparency supported tighter integration between production planning and transportation scheduling. The combined effect of diversified transport modes and digital coordination produced a new operational philosophy. Just-in-time manufacturing sought to minimize inventory by aligning deliveries precisely with production needs. The reason this approach gained prominence is that carrying large inventories ties up capital and increases storage costs. This works because synchronized transport allows goods to arrive shortly before they are required. According to industrial performance studies, firms implementing just-in-time systems often reduced working capital requirements significantly. However, the model also heightened vulnerability to disruption. Natural disasters, labor strikes, or port congestion could interrupt tightly calibrated schedules. Coordination therefore extended into risk management strategies. Firms developed contingency routing plans and diversified supplier bases to mitigate exposure. Transportation and coordination have thus evolved as interdependent pillars of modern supply chains. Infrastructure provides the physical pathways through which goods move. Information systems ensure that these movements occur in structured sequences. The reason global networks function at scale is that both dimensions reinforce one another continuously. Improvements in speed encourage greater specialization across regions. Enhanced coordination allows that specialization to operate without constant breakdown. The supply chain becomes a dynamic system of calibrated motion. Its stability depends on maintaining balance between efficiency and resilience. As trade volumes continue to expand, the pressures on this balance grow more pronounced. The architecture of movement and information remains in constant adaptation. By the late 20th century, global supply chains had reached a level of integration that would have been unimaginable a century earlier. Container ports operated around the clock, processing thousands of standardized units each day. Inland distribution centers functioned as carefully timed transfer points rather than long-term storage sites. Retail shelves in major cities reflected production decisions made months earlier in distant factories. At the time, consumers began to expect constant availability across an expanding range of goods. This expectation placed additional pressure on transportation networks to perform without interruption. Coordination systems grew more sophisticated in response to these rising demands. The supply chain became a continuous operational cycle rather than a sequence of isolated exchanges. The mechanism that sustains such integration depends on layered redundancy and calibrated efficiency. The reason redundancy matters is that complete reliance on a single route or supplier increases systemic fragility. This works because disruption in one location can cascade rapidly through interconnected networks. Firms therefore balance cost minimization with strategic diversification. Secondary suppliers, alternative shipping lanes, and reserve inventory buffers serve as stabilizing elements. Analytical models simulate potential delays and quantify exposure to risk. According to logistics research, diversified routing reduces recovery time after localized disruptions. Coordination systems integrate these contingency plans into routine scheduling processes. Stability emerges from deliberate structural design rather than chance. Global crises have periodically tested the resilience of transportation and coordination networks. Port closures, geopolitical tensions, and public health emergencies have disrupted established routes. The reason these events carry systemic impact is that modern supply chains operate with limited slack. This works because synchronized systems amplify both efficiency and vulnerability. According to economic assessments, temporary shutdowns in key manufacturing regions can reverberate through multiple industries simultaneously. Firms respond by reassessing supplier concentration and inventory policies. Some diversify geographically, while others increase strategic stockpiles of critical components. Coordination technologies assist in reallocating shipments and identifying alternative sources. The architecture of global exchange demonstrates both adaptability and constraint under stress. Despite periodic disruption, the underlying logic of transportation and coordination continues to deepen. Infrastructure investment expands port capacity, modernizes rail corridors, and digitizes customs procedures. Information systems integrate predictive analytics capable of forecasting demand fluctuations and route congestion. The mechanism driving further integration rests on compounding feedback. Efficient transport encourages broader specialization, which in turn increases transport demand. This works because interconnected economies generate mutual dependence across regions. Coordination frameworks evolve to manage rising complexity with greater precision. The supply chain functions as an adaptive organism shaped by technology, policy, and market incentives. Its trajectory reflects sustained effort to harmonize movement and information at global scale. The contemporary global supply chain stands as a synthesis of centuries of transportation innovation and organizational learning. Steam engines, diesel locomotives, cargo aircraft, and digital networks represent successive layers of capability. Each layer expanded the feasible distance between production and consumption. Coordination systems transformed these physical possibilities into structured routines. The reason this synthesis endures lies in its ability to recalibrate under shifting conditions. This works because flexibility is embedded alongside efficiency within modern design principles. Transportation provides motion across geography, while coordination aligns timing across institutions. Together they sustain a system of exchange that links factories, ports, warehouses, and households in continuous sequence. The rhythm of global commerce depends on this carefully maintained synchronization. Global crises have periodically tested the resilience of transportation and coordination networks. Port closures, geopolitical tensions, and public health emergencies have disrupted established routes. The reason these events carry systemic impact is that modern supply chains operate with limited slack. This works because synchronized systems amplify both efficiency and vulnerability. According to economic assessments, temporary shutdowns in key manufacturing regions can reverberate through multiple industries simultaneously. Firms respond by reassessing supplier concentration and inventory policies. Some diversify geographically, while others increase strategic stockpiles of critical components. Coordination technologies assist in reallocating shipments and identifying alternative sources. The architecture of global exchange demonstrates both adaptability and constraint under stress. Despite periodic disruption, the underlying logic of transportation and coordination continues to deepen. Infrastructure investment expands port capacity, modernizes rail corridors, and digitizes customs procedures. Information systems integrate predictive analytics capable of forecasting demand fluctuations and route congestion. The mechanism driving further integration rests on compounding feedback. Efficient transport encourages broader specialization, which in turn increases transport demand. This works because interconnected economies generate mutual dependence across regions. Coordination frameworks evolve to manage rising complexity with greater precision. The supply chain functions as an adaptive organism shaped by technology, policy, and market incentives. Its trajectory reflects sustained effort to harmonize movement and information at global scale. The contemporary global supply chain stands as a synthesis of centuries of transportation innovation and organizational learning. Steam engines, diesel locomotives, cargo aircraft, and digital networks represent successive layers of capability. Each layer expanded the feasible distance between production and consumption. Coordination systems transformed these physical possibilities into structured routines. The reason this synthesis endures lies in its ability to recalibrate under shifting conditions. This works because flexibility is embedded alongside efficiency within modern design principles. Transportation provides motion across geography, while coordination aligns timing across institutions. Together they sustain a system of exchange that links factories, ports, warehouses, and households in continuous sequence. The rhythm of global commerce depends on this carefully maintained synchronization. In earlier chapters, production and transportation expanded across continents, linking factories to distant markets. As output scaled and trade routes lengthened, a new challenge emerged between production and consumption. Goods rarely moved in perfect synchronization with demand. Seasonal cycles, shipping delays, and uneven purchasing patterns created gaps in time. Inventory developed as a buffer against that uncertainty. Warehouses became the physical spaces where time was managed and risk was absorbed. These structures did not simply store products, they stabilized entire supply systems. By holding surplus in strategic locations, firms protected themselves from disruption. The evolution of global supply chains therefore required the deliberate organization of space dedicated to waiting. Waiting became an economic function. The modern warehouse stands as a quiet but essential institution within industrial society. The earliest forms of organized storage were closely tied to agriculture and state authority. By 3000 BCE, centralized granaries operated in regions such as Mesopotamia and Egypt. These facilities protected grain from spoilage and theft while enabling redistribution during scarcity. At the time, inventory represented survival rather than profit optimization. During the Roman Empire, warehouses known as horia lined the ports of Ostia and Rome. These buildings stored olive oil, wine, and grain arriving from across the Mediterranean. According to archaeological records, some horia were built with raised floors and ventilation systems to preserve quality. In medieval Europe, merchant guilds maintained storage houses near city gates and river docks. These spaces reflected growing commercial exchange and the need to bridge production cycles with market days. Storage, even in these early systems, mediated the tension between abundance and absence. As industrial manufacturing accelerated in the 18th and 19th centuries, inventory acquired new economic meaning. Factories produced standardized goods in volumes that exceeded immediate local demand. Railroads and steamships extended distribution networks, but transit times remained unpredictable. The mechanism of buffering through storage reduced the risk of idle machinery and lost sales. Firms held raw materials to prevent production stoppages. They also accumulated finished goods to respond quickly to wholesalers. This works because uncertainty in supply and uncertainty in demand rarely move together. Inventory absorbs fluctuations by converting variable flows into stable availability. Warehouses multiplied near rail junctions and urban centers. By the late 19th century, cities like Chicago and Liverpool contained vast brick storage complexes. These facilities signaled a shift from episodic trade to continuous circulation. The rise of department stores and mail-order catalogs in the late 19th century intensified the importance of warehousing. Companies such as Sears built centralized distribution centers to coordinate national shipments. By 1910, mechanized elevators and conveyor belts were installed in many large storage buildings. At the time, electricity transformed interior layouts by allowing multi-story operations with artificial lighting. Palletization emerged gradually in the early 20th century, standardizing the unit of movement within warehouses. Studies show that standardized handling units significantly reduced labor time and product damage. According to logistics historians, the forklift truck, introduced in the 1920s, reshaped storage density and stacking height. These technological changes altered the geometry of space. Verticality increased, aisles narrowed, and throughput accelerated. Warehousing became an engineering discipline rather than a passive shelter for goods. The economic logic behind inventory management evolved alongside these structural changes. The mechanism centers on balancing holding costs against stockout risk. Holding inventory ties up capital, requires insurance, and occupies physical space. The reason firms still maintain stock lies in the cost of interruption. Lost sales, halted production lines, and damaged customer relationships often exceed storage expenses. This works because the probability of disruption can never be reduced to zero. Companies therefore calculate safety stock based on variability in demand and lead time. Statistical forecasting models estimate expected consumption over defined periods. When variability increases, recommended inventory levels rise. Warehousing thus becomes a quantitative exercise in risk management. Decisions about square footage and shelving are linked directly to financial modeling. After the Second World War, global trade expanded rapidly under new institutional frameworks. The General Agreement on Tariffs and Trade encouraged cross-border exchange. Containerization, pioneered in the 1950s, standardized maritime transport units. By 1966, regular container services connected North America and Europe. At the time, ports redesigned infrastructure to handle large steel boxes rather than loose cargo. Warehouses adapted by integrating loading docks sized for containers. According to maritime industry data, containerization reduced shipping costs dramatically and shortened handling time. This shift increased the geographic reach of supply chains. Inventory could now be positioned closer to consumption markets rather than production sites. Distribution centers emerged on metropolitan peripheries, linked by highways to retail networks. Storage became an active node within a synchronized global grid. The late 20th century introduced a contrasting philosophy known as just-in-time production. Popularized by Japanese manufacturers, particularly Toyota, this approach sought to minimize inventory levels. The mechanism relies on precise scheduling and reliable supplier relationships. Materials arrive shortly before they are needed in assembly. The reason this reduces cost is the elimination of excess stock and wasted space. However, the system depends on stable transportation and accurate demand signals. When disruptions occur, low inventory magnifies vulnerability. This works because buffers have been deliberately removed. Many Western firms adopted similar lean strategies during the 1980s and 1990s. Warehouses did not disappear, but their functions shifted toward cross-docking and rapid turnover. Storage time decreased while coordination intensity increased. In the early 21st century, digital technologies further transformed inventory and warehousing. Barcode scanning and radio frequency identification enabled real-time tracking of individual units. Studies show that data visibility improves forecasting accuracy and reduces shrinkage. Automated storage and retrieval systems now move goods with robotic precision inside large fulfillment centers. These facilities often span millions of square feet and operate continuously. According to industry reports, e-commerce growth has driven demand for warehouses located near urban populations. Speed of delivery has become a competitive differentiator. Inventory is increasingly segmented across multiple nodes to shorten last-mile transit. Warehousing, once defined by stillness, now embodies constant motion and algorithmic coordination. The quiet buildings that hold global commerce together continue to evolve as supply chains stretch across ever wider distances. As global supply chains matured, the physical warehouse evolved into a complex coordination center. Facilities were no longer designed solely to hold goods, but to regulate their movement with precision. Layout planning became a strategic decision tied to product velocity and order patterns. Fast-moving items were positioned near dispatch zones to reduce travel time. Slower inventory was placed in higher racks or more distant aisles. This spatial logic reduced internal friction and increased throughput. The mechanism of slotting, which assigns products to optimal locations, emerged as a data-driven discipline. Engineers measured pick frequency, weight, and cube dimensions to refine placement. The reason such precision mattered was the scale of operations now involved. In large distribution centers, small inefficiencies multiplied across thousands of daily transactions. Warehousing became an exercise in continuous optimization. Labor organization changed alongside these architectural shifts. Early warehouses relied on manual handling and basic supervision. Over time, Workflow systems standardized tasks into repeatable sequences. Pickers followed defined routes generated by warehouse management software. Supervisors monitored performance through metrics such as picks per hour and order accuracy. This works because measurement transforms abstract activity into comparable units. When performance is visible, managers can adjust staffing and redesign processes. Cross-training reduced vulnerability to absenteeism and seasonal surges. Temporary labor pools expanded during peak demand periods, particularly in retail cycles. According to logistics studies, labor often represents the largest variable cost within warehouse operations. The drive for efficiency therefore focused heavily on human movement and task coordination. The modern warehouse reflects a blend of physical engineering and organizational design. Risk management increasingly shaped decisions about inventory positioning. Companies faced uncertainties ranging from supplier failure to natural disasters. The mechanism of geographic diversification spread stock across multiple facilities. If one region experienced disruption, others could compensate. The reason this approach gained prominence lies in the growing complexity of global sourcing. Components might originate in one continent, be assembled in another, and sold in a third. This interdependence amplified exposure to localized shocks. Safety stock calculations incorporated not only demand variability but geopolitical risk. Insurance markets adapted to cover stored goods against fire, flood, and theft. According to supply chain analysts, resilience requires balancing redundancy with cost discipline. Warehouses therefore became strategic buffers embedded within broader contingency planning. Technological integration deepened in the late 20th and early 21st centuries. Warehouse management systems synchronized inventory records with enterprise resource planning platforms. Real-time data exchange reduced discrepancies between physical stock and digital records. This works because information latency often creates costly errors. When systems communicate instantly, replenishment triggers can be automated. Radio frequency scanners validated each movement within the facility. According to industry research, error rates decline significantly when manual paperwork is eliminated. Automation expanded beyond tracking into physical handling. Conveyors, sortation systems, and robotic arms accelerated repetitive tasks. The reason automation spread unevenly relates to capital intensity and product variety. Highly standardized goods favored mechanization, while diverse assortments required flexible human judgment. E-commerce introduced new operational pressures that reshaped warehouse design. Traditional retail distribution shipped large pallets to storefronts. Online commerce required individual order picking and parcel preparation. This shift multiplied the number of outbound transactions dramatically. The mechanism of zone picking divided facilities into specialized areas to manage complexity. Workers retrieved specific items which were later consolidated for shipment. The reason this structure improved efficiency lies in reduced walking distance and parallel processing. Packaging stations integrated labeling, invoicing, and quality checks into streamlined flows. According to market data, customer expectations for rapid delivery shortened acceptable processing windows. Warehouses responded by extending operating hours and investing in advanced forecasting tools. Inventory visibility became essential to meeting promised delivery times. Environmental considerations gradually entered the warehousing conversation. Large facilities consume significant energy for lighting, heating, and cooling. The mechanism of energy-efficient design reduced long-term operating costs. LED lighting systems replaced older fixtures to cut electricity usage. Insulated walls and reflective roofing moderated temperature fluctuations. This works because climate control directly affects product integrity and worker comfort. Some companies installed solar panels on expansive rooftop surfaces. According to sustainability reports, green certifications improved corporate reputation and investor confidence. Waste reduction programs minimized packaging materials and improved recycling rates. The environmental footprint of warehousing became part of broader corporate responsibility strategies. Operational efficiency and ecological awareness began to intersect. Financial accounting practices also evolved to reflect inventory's strategic importance. Inventory appears on balance sheets as a current asset. Its valuation influences reported profitability and tax obligations. The mechanism of cost flow assumptions, such as first in, first out or weighted average, shapes financial outcomes. The reason accounting method selection matters lies in fluctuating input prices. During inflationary periods, valuation choices affect cost of goods sold calculations. Auditors monitor physical counts to ensure reported figures match reality. According to financial standards boards, accurate inventory reporting underpins investor confidence. Misstatements can distort earnings and undermine trust. Warehousing operations therefore intersect directly with corporate governance. The physical management of goods connects to abstract financial representation. Global supply chains now operate within an environment of heightened uncertainty and rapid change. Pandemics, trade disputes, and climate events have tested the limits of lean inventory models. Companies reassess the balance between efficiency and resilience. The mechanism of strategic stockpiling has re-entered executive discussions. The reason for renewed emphasis on buffers lies in recent disruptions that exposed fragile linkages. Some firms increase domestic warehousing capacity to reduce dependency on distant suppliers. Others invest in advanced analytics to anticipate demand swings more accurately. According to industry surveys, hybrid models blending lean principles with targeted redundancy are gaining traction. Warehousing remains central to this recalibration. As goods pause within these structured spaces, decisions about time, risk, and capital continue to shape the architecture of global exchange. The contemporary warehouse increasingly resembles a technological platform rather than a static storage hall. Sensors embedded in shelving units record movement at granular levels. Cloud-based systems aggregate data across networks of facilities. This constant flow of information transforms inventory from a physical count into a dynamic stream. The mechanism of predictive analytics identifies patterns before they become visible to managers. Algorithms estimate reorder points based on historical sales, weather data, and promotional calendars. The reason predictive tools matter lies in compressed delivery expectations and volatile demand cycles. Firms that anticipate shifts earlier can reposition stock preemptively. This works because time remains the core variable within supply chains. Warehouses now function as nodes within digital ecosystems, responding to signals that originate far beyond their walls. Automation continues to reshape internal operations at increasing scale. Autonomous mobile robots transport bins between storage racks and picking stations. These machines navigate using mapping software and onboard sensors. Human workers remain present, but their roles shift toward oversight and exception handling. The mechanism of goods-to-person systems reduces walking time dramatically. Workers stand at ergonomic stations while items arrive automatically. The reason productivity rises under this model lies in reduced physical strain and repetitive travel. Studies show that such systems can double or triple picking rates in high-volume environments. Capital investment remains substantial, limiting adoption among smaller firms. Yet competitive pressure encourages gradual integration even in mid-sized operations. Warehousing becomes a laboratory for human-machine collaboration. Urbanization has introduced spatial constraints that influence storage strategy. Large distribution centers once clustered in remote industrial zones. Rising land values near metropolitan cores alter that geography. The mechanism of micro-fulfillment centers places compact facilities closer to dense populations. These sites prioritize rapid turnover and limited assortments. The reason proximity matters lies in last-mile delivery costs, which often exceed upstream transportation expenses. Shorter distances reduce fuel consumption and delivery time. This works because consumer expectations increasingly center on same-day or next-day service. Vertical construction has reappeared in certain cities where horizontal expansion is impossible. Multi-story warehouses integrate freight elevators and reinforced floors to manage load distribution. Urban warehousing represents an adaptation to demographic concentration. Climate volatility and geopolitical tension now factor prominently into inventory planning. Floods, wildfires, and storms disrupt transportation corridors with growing frequency. The mechanism of scenario modeling evaluates potential disruptions before they occur. Companies simulate port closures or border restrictions to estimate inventory exposure. The reason modeling has become common practice lies in the cost of recent global shocks. Prolonged supply interruptions revealed vulnerabilities embedded in lean systems. This works because digital twins of supply networks allow managers to test responses virtually. Diversified sourcing and regional warehousing reduce dependence on single routes. Strategic reserves of critical components reappear in industries such as pharmaceuticals and semiconductors. Warehousing adapts as a protective layer within uncertain global conditions. Financial markets also respond to the expanding significance of storage infrastructure. Real estate investment trusts increasingly specialize in logistics properties. Warehouses become assets traded on public exchanges. The mechanism of long-term leasing agreements provides stable income streams for investors. The reason capital flows toward logistics lies in sustained growth of global trade and e-commerce. According to market analysts, vacancy rates in prime logistics hubs often remain low despite economic cycles. Institutional investors view distribution centers as essential infrastructure rather than discretionary assets. This works because supply chains underpin nearly every sector of the economy. As investment increases, facility design standards rise to attract high-quality tenants. Warehousing becomes intertwined with financial strategy at macroeconomic scale. Regulatory frameworks influence how inventory moves across borders and within nations. Customs procedures, safety standards, and tax policies shape warehouse location decisions. The mechanism of bonded warehouses allows goods to be stored without immediate payment of import duties. This arrangement provides flexibility for re-export or deferred taxation. The reason such facilities exist lies in the desire to encourage trade while maintaining oversight. Compliance systems track product origin and classification codes meticulously. According to trade authorities, accurate documentation reduces delays and penalties. Environmental regulations also dictate handling of hazardous materials. Warehouses storing chemicals or pharmaceuticals must meet stringent safety protocols. Legal structures therefore embed storage facilities within broader governance systems. Social dynamics within warehouses remain significant despite technological transformation. Large fulfillment centers employ thousands of workers during peak seasons. Labor conditions, wage structures, and scheduling practices attract public scrutiny. The mechanism of performance monitoring through wearable devices or scanning metrics generates debate. Managers argue that data improves fairness and efficiency. Critics contend that constant surveillance increases stress and reduces autonomy. This works because productivity targets translate abstract corporate goals into daily routines. Collective bargaining efforts and regulatory oversight attempt to balance efficiency with worker well-being. According to labor researchers, warehouse employment often reflects broader economic shifts toward service and logistics sectors. The human dimension persists within automated environments. Inventory and warehousing now occupy a central position in the architecture of global commerce. Goods pause within structured spaces before resuming their journeys across oceans and highways. Each pause represents a calculated decision about timing, cost, and risk. The mechanism of coordination extends from factory floors to consumer doorsteps. The reason warehousing endures, despite efforts to minimize stock, lies in persistent uncertainty. Supply chains stretch across political boundaries and natural landscapes that remain unpredictable. This works because buffers absorb shocks that cannot be eliminated entirely. As digital systems refine forecasting and automation enhances precision, the fundamental role of storage continues. Warehouses stand quietly at the intersection of production and consumption, holding the rhythm of exchange in measured suspension as global networks expand toward new frontiers. In earlier phases of industrial expansion, firms concentrated production close to domestic markets, relying on regional suppliers and predictable transport corridors. Over time, rising labor costs, expanding trade agreements, and advances in container shipping altered that geography. Production gradually dispersed across continents as companies searched for cost efficiencies and specialized capabilities. This shift did not occur randomly but followed patterns shaped by infrastructure, political stability, and access to skilled labor. By the late 20th century, multinational corporations were coordinating activities in dozens of countries simultaneously. Supply chains evolved from linear sequences into intricate global networks with multiple sourcing nodes. The architecture of these networks reflected both economic calculation and institutional trust. Firms no longer viewed sourcing as a transactional purchase but as a strategic design choice embedded in corporate structure. The scale of coordination required new forms of management, communication, and risk assessment. The mechanism behind global sourcing structures rests on comparative advantage and cost arbitrage. The reason companies distribute production internationally is that input prices, wages, regulatory environments, and currency values differ across borders. This works because transportation costs decline dramatically with the standardization of shipping containers and improvements in logistics software. When movement becomes cheaper and more predictable, geographic distance loses some of its constraint. Firms can separate design, component manufacturing, assembly, and distribution into specialized locations optimized for each function. Procurement departments analyze supplier clusters, tariff regimes, and lead times before establishing contracts. Over time, repeated transactions create durable relationships that stabilize expectations. These relationships reduce uncertainty, which in turn lowers the perceived risk of long-distance coordination. Global sourcing structures therefore emerge from layered calculations rather than isolated decisions. By the 1970s, export-oriented manufacturing zones were expanding rapidly in East Asia. Governments in countries such as South Korea and Taiwan invested heavily in ports, industrial parks, and technical education. At the time, multinational firms were searching for alternatives to higher-cost production centers in North America and Western Europe. By 1980, special economic zones in China began attracting foreign direct investment under newly liberalized policies. These zones offered tax incentives, simplified customs procedures, and infrastructure tailored for export manufacturing. According to trade data from the period, manufactured exports from East Asia grew at rates exceeding global averages. The concentration of suppliers within designated regions created dense industrial ecosystems. Component makers, logistics providers, and financial institutions clustered together, reinforcing one another's efficiency. The historical trajectory of these zones illustrates how policy frameworks can reshape global sourcing patterns over a single generation. As sourcing extended outward, corporations adopted modular production systems that divided complex products into standardized components. The mechanism of modularity allows different suppliers to manufacture parts independently while adhering to shared specifications. This works because digital design files and quality standards can be transmitted instantly across continents. A firm headquartered in one country may design a product, contract components from multiple regions, and coordinate final assembly elsewhere. The reason this structure persists is that specialization improves efficiency and accelerates innovation. Suppliers focus on narrow competencies and invest deeply in process optimization. Over time, knowledge accumulates within regional clusters, strengthening their global competitiveness. The modular approach also increases flexibility by allowing firms to substitute suppliers if disruptions occur. However, this same dispersion can amplify vulnerability when disruptions affect entire regions simultaneously. Financial systems play a central role in sustaining global sourcing arrangements. Letters of credit, trade finance instruments, and currency hedging contracts facilitate transactions across legal jurisdictions. According to the World Trade Organization, the expansion of multilateral trade agreements in the 1990s reduced tariff barriers and clarified dispute resolution mechanisms. These institutional frameworks lowered transaction costs and encouraged cross-border investment. Studies show that predictable legal environments correlate strongly with sustained foreign direct investment flows. The reason is that long-term supplier relationships require confidence in contract enforcement. Insurance markets further mitigate risk by covering cargo loss, political instability, and payment defaults. The integration of finance with logistics creates a system in which goods and capital circulate in parallel. Without these financial supports, the geographic spread of sourcing would be significantly constrained. By the early 2000s, digital platforms were reshaping procurement practices. Enterprise resource planning systems connected headquarters to factories and suppliers in real time. At the time, broadband internet and satellite communication reduced information lag between continents. Procurement managers gained visibility into inventory levels, shipment status, and production schedules across multiple time zones. According to industry surveys, companies that integrated digital tracking systems reported measurable reductions in inventory holding costs. The clustering of data analytics with logistics planning increased forecasting accuracy. These developments enabled firms to implement just-in-time delivery models on a global scale. However, lean inventory strategies also reduced buffers against unexpected shocks. The structural emphasis on efficiency sometimes came at the expense of resilience. Global sourcing structures continue to evolve under shifting geopolitical and environmental pressures. Trade tensions, pandemic disruptions, and climate-related events have exposed the fragility of extended supply lines. Firms are reassessing supplier concentration and exploring diversified or regionalized alternatives. The mechanism of dual sourcing, in which companies maintain multiple suppliers for critical components, is gaining renewed attention. This works because redundancy can limit exposure to localized disruptions. The reason such strategies are costly is that maintaining parallel relationships reduces economies of scale. Nevertheless, corporations increasingly treat resilience as a strategic asset rather than a secondary concern. The architecture of global sourcing is therefore entering a new phase defined by balance between efficiency and security. As global sourcing networks matured, firms began distinguishing between strategic and transactional suppliers within their portfolios. Strategic suppliers were integrated into long-term planning processes and often participated in product development cycles. Transactional suppliers, by contrast, were selected primarily on price and short-term availability. This differentiation reshaped procurement departments, transforming them from purchasing offices into analytical hubs. Data regarding cost structures, capacity utilization, and geopolitical exposure became central to sourcing decisions. Over time, supplier scorecards emerged to measure quality consistency, delivery reliability, and compliance with labor standards. These metrics allowed corporations to rank partners across regions using standardized criteria. The architecture of global sourcing thus evolved into a tiered hierarchy with varying degrees of dependence. First-tier suppliers often coordinated their own upstream networks, creating layered chains of responsibility. Visibility into second- and third-tier operations gradually became a priority as disruptions revealed hidden interdependencies. The mechanism of multi-tier sourcing operates through cascading contracts and shared technical specifications. Lead firms establish requirements that propagate through successive layers of subcontractors. This works because digital documentation and compliance audits can standardize expectations across geographically dispersed facilities. The reason complexity increases is that each additional tier introduces variability in regulation, infrastructure, and managerial practice. When visibility weakens beyond the first tier, risk accumulates in unseen segments of the chain. Corporations respond by implementing traceability systems that map component origins and production pathways. These systems rely on barcode tracking, blockchain ledgers, and centralized databases to consolidate information. The goal is not complete control but improved transparency during disruptions. Over time, transparency itself becomes a competitive advantage because it reassures investors and customers. Multi-tier sourcing therefore reflects both efficiency objectives and accountability pressures. Regional specialization further shapes the structure of global sourcing. Certain regions develop reputations for electronics assembly, precision tooling, or textile production based on accumulated expertise. At the time industrial clusters solidify, educational institutions, infrastructure investment, and supplier density reinforce one another. By the early 21st century, coastal provinces in China had become central to consumer electronics manufacturing. Simultaneously, automotive component production expanded across parts of Mexico to serve North American markets. According to the United Nations Conference on Trade and Development, foreign direct investment flows often concentrate in regions with established supplier ecosystems. This concentration reduces onboarding time for new entrants and lowers coordination costs. However, geographic clustering can magnify exposure to natural disasters or policy shifts. The balance between specialization and diversification remains a defining tension in sourcing design. Contractual governance mechanisms underpin these geographically dispersed relationships. Master service agreements define quality thresholds, intellectual property protections, and dispute resolution procedures. This works because clearly articulated expectations reduce ambiguity in cross-border transactions. The reason contracts alone are insufficient is that enforcement across jurisdictions can be slow or uncertain. Firms therefore supplement formal agreements with relational governance based on repeated interaction and mutual dependence. Long-term partnerships encourage suppliers to invest in dedicated equipment and workforce training. Such investments increase switching costs, deepening interdependence between buyer and supplier. Trust accumulates gradually through consistent performance and transparent communication. Nevertheless, power imbalances often favor lead firms that control brand access and distribution channels. Governance within global sourcing structures thus combines legal formality with negotiated flexibility. Cost management strategies continue to influence sourcing architecture. Companies analyze total landed cost rather than unit price alone, incorporating transportation, tariffs, insurance, and inventory holding expenses. This works because a low factory gate price may be offset by high logistics or compliance costs. The mechanism of should-cost modeling estimates what a component ought to cost based on material inputs and process efficiency. Procurement teams use these models to negotiate with suppliers and benchmark performance across regions. According to industry research, firms that integrate total cost analysis achieve more stable margins during currency fluctuations. Currency volatility itself shapes sourcing decisions by altering relative competitiveness. Hedging strategies can mitigate short-term swings but cannot eliminate structural differences in labor or energy pricing. Over time, sourcing maps are redrawn as cost equations shift. Environmental and social governance standards increasingly intersect with sourcing design. Corporations face scrutiny from regulators, investors, and consumers regarding labor conditions and carbon emissions embedded in supply chains. This works because reputational risk can translate into financial loss through boycotts or restricted market access. The reason monitoring expands is that downstream brands are often held accountable for upstream practices. Audits, certification schemes, and sustainability reporting frameworks attempt to standardize evaluation criteria. Digital traceability tools enable companies to track raw material origins and production footprints. According to sustainability studies, transparency can reduce instances of labor violations when combined with enforcement mechanisms. However, compliance requirements raise operating costs for smaller suppliers. Balancing ethical oversight with economic inclusion remains a persistent challenge. As global sourcing structures adapt to technological change, automation alters the calculus of location. Robotics and advanced manufacturing systems reduce reliance on low-wage labor in certain industries. This works because capital-intensive production narrows cost differentials between regions. The reason reshoring becomes plausible in some sectors is that transportation and coordination costs may outweigh residual labor savings. Nevertheless, many industries still depend on dense supplier ecosystems that cannot be replicated quickly. Infrastructure depth, workforce experience, and regulatory familiarity anchor production in established hubs. Firms therefore evaluate sourcing strategies through a dynamic lens rather than a static model. Efficiency, resilience, compliance, and innovation all factor into the equation simultaneously. The architecture of global sourcing continues to evolve as these variables shift in relative importance. As global sourcing structures matured, firms increasingly relied on lead firms to orchestrate vast cross-border production systems. These lead firms controlled branding, product design, and access to consumer markets while outsourcing much of the manufacturing process. This arrangement created what analysts describe as buyer-driven value chains. In such systems, contractual authority flowed downward from headquarters to first-tier suppliers and then through successive subcontractors. The concentration of strategic control at the top allowed corporations to respond quickly to changing consumer demand. At the same time, operational risk was distributed across multiple independent producers. The mechanism reduced capital intensity for brand owners while preserving flexibility in output levels. Over time, coordination required standardized reporting formats, synchronized production schedules, and harmonized compliance audits. Digital dashboards aggregated performance data from factories operating in different regulatory environments. The result was a governance structure that blended centralized oversight with decentralized execution across continents. The reason buyer-driven systems expanded rapidly in the late 20th century lies partly in retail consolidation. Large retail chains in markets such as the United States and Western Europe demanded consistent quality at predictable prices. This works because scale purchasing grants retailers bargaining leverage over manufacturers. Suppliers seeking access to these markets accepted tighter margins in exchange for volume stability. According to the Organization for Economic Cooperation and Development, trade liberalization agreements during the 1990s reinforced this shift by reducing tariffs on manufactured goods. Lower trade barriers encouraged retailers and brand owners to source from geographically distant producers. The clustering of demand within major consumer markets shaped production patterns thousands of miles away. Over time, sourcing strategies aligned closely with retail calendars and promotional cycles. This alignment deepened interdependence between distribution networks and upstream manufacturing hubs. Parallel to buyer-driven chains, producer-driven networks emerged in capital-intensive industries. In sectors such as aerospace, advanced machinery, and pharmaceuticals, manufacturing capabilities remained concentrated within specialized firms. These firms controlled proprietary technologies and invested heavily in research and development. The mechanism of producer-driven sourcing emphasizes vertical coordination around technical standards and intellectual property protection. This works because complex products require precise integration of components engineered to exact tolerances. At the time large aircraft manufacturers expanded global partnerships, they relied on certified suppliers with proven expertise. By 2010, companies such as Boeing and Airbus coordinated production across dozens of countries. According to industry reports, final assembly represented only a fraction of total production value. The majority of value creation occurred within specialized component manufacturing clusters. Producer-driven sourcing therefore concentrates authority around technological capability rather than retail access. Financialization further reshaped global sourcing structures during the early 21st century. Institutional investors evaluated corporations based on return on invested capital and asset efficiency. This works because financial markets reward firms that minimize fixed assets while maintaining revenue growth. The reason outsourcing accelerated in some industries was that contract manufacturing reduced balance sheet exposure. Companies divested factories and transferred operational responsibility to specialized suppliers. Private equity ownership of logistics providers and component manufacturers introduced additional performance pressures. According to market analyses, supply chain decisions increasingly reflected shareholder expectations alongside operational considerations. Working capital optimization became a central metric in procurement strategy. Inventory reduction, extended payment terms, and supplier financing programs altered cash flow dynamics across tiers. Financial incentives thus reinforced the structural dispersion of production activities. Risk management practices gained prominence after repeated disruptions exposed structural fragility. Natural disasters, trade disputes, and public health emergencies interrupted flows of components across multiple sectors. The mechanism of risk mapping identifies geographic concentration and single-source dependencies within sourcing portfolios. This works because quantitative modeling can simulate the impact of localized shocks on global throughput. Firms began developing contingency plans that included safety stock buffers and alternative supplier qualification. At the time semiconductor shortages constrained automotive production, manufacturers reassessed just-in-time principles. According to the International Monetary Fund, Supply chain disruptions contributed to inflationary pressures in several economies. The clustering of critical component production within limited regions amplified these effects. Diversification strategies now factor political stability and climate vulnerability into site selection. Resilience has become an explicit design criterion alongside cost efficiency. Digital transformation continues to redefine the architecture of sourcing coordination. Cloud-based platforms integrate procurement, logistics, and compliance data into unified interfaces accessible across time zones. This works because standardized data protocols enable interoperability between independent enterprise systems. The reason predictive analytics matter is that demand forecasting influences production scheduling months in advance. Machine learning models analyze historical sales patterns, transportation delays, and macroeconomic indicators. According to technology adoption surveys, firms using advanced analytics report improved order fulfillment accuracy. Blockchain pilots attempt to enhance traceability for high-value or regulated goods. Internet of Things sensors monitor shipment conditions and relay temperature or location data in real time. These tools strengthen visibility but also increase dependence on digital infrastructure. Cybersecurity considerations therefore intersect directly with sourcing reliability. Global sourcing structures now operate within an environment shaped by geopolitical recalibration and environmental constraint. Trade realignments encourage regional trade blocs and localized production networks in certain sectors. This works because governments view supply security as a component of national resilience. The reason nearshoring initiatives attract attention is that proximity can shorten lead times and reduce exposure to border disruptions. Nevertheless, deeply embedded supplier ecosystems cannot be relocated without significant transition costs. Infrastructure investment, workforce training, and regulatory harmonization requires sustained commitment over many years. Corporations weigh these structural realities against political signals and market incentives. The global sourcing system remains dynamic rather than static, continuously adapting to shifting constraints and opportunities. Its future configuration will reflect the balance struck between integration and autonomy across regions. In the late 20th century, corporations began to view supply chains not simply as operational necessities but as strategic architectures. Production, transportation, warehousing, and procurement were no longer treated as separate administrative functions. They were redesigned as interconnected systems governed by centralized planning. This shift reflected the growing scale of multinational firms whose activities spanned continents. As trade barriers declined and communication technologies improved, firms could coordinate complex operations across time zones. The supply chain became a deliberate design project shaped by corporate leadership. Executives invested in mapping flows of materials from raw extraction to final consumption. They sought to understand not only costs but also timing, reliability, and risk. What emerged was a philosophy of integration that aimed to align every logistical decision with broader corporate objectives. The mechanism behind corporate supply chain design relied on visibility and control. The reason visibility mattered was that fragmented information created delays and excess inventory. Firms implemented enterprise resource planning systems that linked sales forecasts to production schedules. This works because digital coordination reduces uncertainty between departments and external suppliers. When demand data flows instantly from retailers to manufacturers, production can adjust in near real time. The mechanism also depends on standardized metrics such as lead time, fill rate, and total landed cost. These metrics allow managers to compare performance across regions and suppliers. Analytical teams model transportation routes and capacity constraints to identify bottlenecks. Decisions about factory location, sourcing strategy, and distribution networks are then optimized through quantitative tools. The supply chain becomes a design system rather than an inherited arrangement. By the 1980s, corporations in the United States and Europe had embraced global sourcing strategies. At the time, containerization had already reduced maritime shipping costs dramatically. The spread of standardized containers following their introduction by Malcolm McLean in the 1950s enabled seamless transfers between ships, trucks, and trains. By 1990, major ports in Shanghai, Rotterdam, and Los Angeles had become central nodes in global trade networks. Corporations redesigned their supply chains around these hubs. Manufacturing migrated toward regions offering lower labor costs and supportive industrial policies. According to trade data from the period, cross-border flows of intermediate goods grew faster than final consumer goods. The architecture of supply chains shifted from national to transnational structures within a single generation. Corporate supply chain design also introduced tiered supplier systems. Lead firms established primary partners responsible for assembling complex components. These first-tier suppliers then coordinated networks of second- and third-tier producers. The mechanism reduces administrative burden on the lead firm while preserving oversight through contractual standards. This works because responsibility cascades through the hierarchy while performance metrics flow upward. Quality control systems were embedded at each level to maintain consistency across thousands of transactions. Contracts specified delivery windows, defect thresholds, and contingency procedures. Firms developed dual sourcing strategies to mitigate disruptions from a single provider. The resulting structure resembled a managed ecosystem in which autonomy existed within defined parameters. Technological integration became a defining feature of this design philosophy. Barcode scanning and later radio frequency identification enabled precise tracking of goods in transit. Data collected at distribution centers fed into centralized dashboards. The reason this mattered was that inventory represented both capital and risk. Excess stock tied up financial resources, while shortages damaged customer relationships. This works because predictive analytics can anticipate fluctuations in demand based on historical patterns. According to studies from logistics research institutions, firms that implemented real-time tracking systems reduced inventory carrying costs significantly. Digital platforms allowed procurement teams to evaluate supplier performance continuously rather than periodically. Over time, information technology became inseparable from physical logistics infrastructure. By the early 2000s, supply chain design incorporated risk management as a formal discipline. At the time, corporations had experienced disruptions caused by natural disasters and geopolitical tensions. The 1997 Asian financial crisis revealed vulnerabilities in concentrated sourcing models. After the attacks of September 11, 2001, governments introduced new security requirements that altered transportation flows. Firms responded by diversifying supplier bases and increasing safety stock in critical categories. According to policy analyses, regulatory compliance costs became a measurable component of supply chain planning. Scenario modeling tools evaluated the probability and impact of disruptions across regions. Corporate boards began to view resilience as complementary to efficiency rather than contradictory. Design decisions increasingly balanced cost minimization with strategic flexibility. The mechanism of flexibility involves maintaining optional capacity and alternative routes. This works because uncertainty is inherent in global systems characterized by political shifts and fluctuating demand. Firms evaluated trade-offs between centralized megafactories and distributed regional plants. Centralization offered economies of scale but heightened exposure to localized shocks. Regionalization reduced transit times and currency risks but required redundant investments. Analytical models quantified these trade-offs using simulations of demand volatility and transport delays. Executives interpreted these models through the lens of shareholder expectations and competitive positioning. Corporate supply chain design thus became an ongoing process rather than a one-time blueprint. As corporate supply chains matured, financial strategy became deeply embedded within logistical design. Capital allocation decisions began shaping where factories were built and how inventories were managed. Firms analyzed working capital cycles to determine how quickly cash moved through procurement, production, and sales. The objective was to shorten this cycle without sacrificing reliability. Inventory optimization models calculated the precise quantity required to meet service targets while minimizing storage expense. Financial controllers worked alongside operations managers to align cost accounting with physical flows. Transfer pricing policies influenced sourcing decisions across subsidiaries in different tax jurisdictions. Currency fluctuations introduced additional layers of complexity into procurement contracts. The supply chain evolved into a financial instrument as much as a physical network. The mechanism linking finance and logistics operates through cost visibility and performance measurement. Activity-based costing assigns expenses to specific stages of production and distribution. This works because granular data reveals inefficiencies that aggregated accounting would obscure. Managers can identify which routes generate excess handling costs or which suppliers create hidden delays. Performance dashboards translate operational data into return on investment metrics. The reason these metrics matter is that executive incentives often depend on financial ratios. When logistics improvements improve asset turnover or margin stability, they gain organizational support. Analytical modeling integrates transportation rates, tariff structures, and labor costs into unified simulations. Decision makers evaluate scenarios not only for operational feasibility but also for earnings impact. Corporate supply chain design thus reflects a continuous negotiation between operational realism and financial expectation. Outsourcing became a defining characteristic of late 20th century supply networks. Corporations increasingly relied on contract manufacturers and third-party logistics providers. At the time, deregulation in transportation sectors allowed specialized firms to compete aggressively on price. By the 1990s, large logistics companies offered integrated services that included warehousing, freight forwarding, and customs brokerage. Firms shifted non-core activities to external partners to concentrate on branding and product development. According to industry reports from that period, outsourcing reduced fixed capital investments while increasing scalability. The architecture of supply chains expanded beyond corporate boundaries into complex webs of contractual relationships. Legal agreements specified performance standards, liability terms, and dispute resolution mechanisms. Governance structures evolved to manage these extended networks effectively. Coordination across outsourced networks required new forms of communication infrastructure. Electronic data interchange systems standardized document exchange between firms. Purchase orders, invoices, and shipping notices could move digitally rather than through paper processes. This works because standardized formats reduce interpretation errors and administrative delay. Cloud-based platforms later enabled real-time collaboration across continents. The reason collaboration matters is that delays often originate from misaligned expectations rather than physical constraints. Shared forecasting systems allowed suppliers to anticipate demand shifts before orders were finalized. Performance scorecards created transparency around delivery reliability and quality metrics. Trust developed gradually as data accuracy improved and contractual disputes declined. The supply chain became an information ecosystem sustained by mutual dependency. Strategic sourcing methodologies further refined corporate supply chain design. Procurement teams categorized inputs according to criticality and substitutability. Commoditized goods were subjected to competitive bidding processes to extract price advantages. Strategic components with limited suppliers were managed through long-term partnerships. This works because differentiated treatment aligns risk exposure with negotiation leverage. The mechanism emphasizes relationship management alongside cost control. Supplier development programs invested in training and technology upgrades for key partners. According to research in operations management, collaborative partnerships improved innovation rates and defect reduction. Procurement ceased to function as a purely transactional department and instead assumed a strategic advisory role. Decisions about supplier geography incorporated political stability, infrastructure quality, and labor market depth. Environmental and social considerations gradually entered supply chain design frameworks. By the early 2000s, public scrutiny of labor conditions influenced sourcing strategies. Firms conducted audits to verify compliance with safety and wage standards. Regulatory regimes in multiple countries required disclosure of sourcing practices. This works because transparency reduces reputational risk and strengthens stakeholder trust. Carbon accounting systems measured emissions across transportation and production stages. Companies evaluated trade-offs between distant low-cost production and closer higher-cost manufacturing with reduced environmental impact. According to sustainability studies, integrated reporting improved long-term risk assessment. Ethical sourcing policies became embedded within supplier contracts and performance evaluations. Corporate supply chains began reflecting broader societal expectations alongside economic imperatives. Digital transformation accelerated the analytical depth of corporate supply chain management. Advanced planning systems incorporated machine learning algorithms to forecast demand variability. The mechanism relies on historical data combined with external indicators such as economic trends. This works because predictive accuracy improves when diverse datasets are integrated systematically. Automated warehouses utilized robotics to reduce labor dependency and increase throughput consistency. Sensors embedded within shipments transmitted location and temperature information continuously. The reason continuous monitoring matters is that deviations can be corrected before they escalate into systemic failures. Blockchain technologies were piloted to enhance traceability across multi-tier supplier networks. Data governance policies established standards for privacy and cybersecurity across global operations. The supply chain became a digitally mediated structure layered upon physical infrastructure. Design choices increasingly reflected geopolitical awareness and strategic autonomy. Trade tensions and shifting alliances influenced sourcing diversification. Firms reassessed reliance on single regions for critical inputs. The mechanism of diversification involves distributing production across multiple jurisdictions. This works because exposure to regulatory change is reduced when operations are geographically balanced. Regional trade agreements shaped tariff structures and market access conditions. Companies analyzed long-term demographic trends to anticipate labor availability and consumer demand. Infrastructure investment patterns signaled emerging logistics corridors and industrial clusters. Corporate planners interpreted these signals within multi-decade investment horizons. Supply chain design continued evolving as a dynamic response to economic, technological, and political transformation. As corporate supply chain design entered the second decade of the 21st century, resilience became inseparable from efficiency. For decades, lean production models had prioritized minimal inventory and tightly synchronized delivery schedules. These systems reduced waste and improved capital utilization under stable conditions. However, increasing complexity exposed vulnerabilities that were not fully visible in earlier optimization models. Firms began reassessing assumptions about predictability and continuity. The global financial crisis of 2008 had already revealed how quickly demand could contract across interconnected markets. Supply chain leaders responded by embedding contingency planning into routine decision-making. Buffer capacity, alternate suppliers, and flexible contracts gained renewed attention. Efficiency remained important, but resilience emerged as a parallel design objective. The mechanism of resilience operates through redundancy and adaptability. Redundancy involves maintaining backup suppliers, transportation routes, and inventory reserves. This works because failures in one node do not automatically cascade through the entire system. Adaptability depends on rapid information flows and decentralized decision authority. When local managers can adjust procurement or distribution plans quickly, disruptions are contained more effectively. The reason decentralized response matters is that centralized approval can introduce delay during crises. Scenario planning exercises simulate potential shocks ranging from natural disasters to regulatory changes. Analytical tools estimate the financial impact of downtime across production stages. Corporate supply chain design increasingly treats uncertainty as a permanent condition rather than an exception. By 2020, global supply networks faced a disruption of unprecedented scale during the COVID-19 pandemic. At the time, lockdown measures in major manufacturing regions halted production simultaneously. Port congestion intensified as health restrictions slowed cargo handling operations. According to international trade statistics, global merchandise trade volumes declined sharply in early 2020 before gradually recovering. Corporations confronted shortages of semiconductors, medical supplies, and consumer goods. Governments implemented export controls on critical products, altering established trade flows. The concentration of component manufacturing in specific regions amplified bottlenecks. Firms accelerated diversification strategies that had previously progressed slowly. The pandemic served as a structural stress test for corporate supply chain design. Digital visibility tools played a crucial role during this period of disruption. Real-time tracking systems allowed firms to monitor shipments delayed at congested ports. Predictive analytics assessed inventory depletion rates across distribution centers. This works because early detection enables proactive reallocation of stock between regions. Control towers, centralized dashboards integrating multi-source data, became common organizational features. The reason integration matters is that fragmented information limits coordinated response. Machine learning models recalibrated demand forecasts based on rapidly shifting consumer behavior. According to industry surveys, companies with advanced analytics capabilities recovered operational stability more quickly. Digital infrastructure proved as essential as physical logistics assets. Corporate design strategies also incorporated regionalization trends. Firms evaluated the benefits of locating production closer to end markets. Nearshoring initiatives shifted certain manufacturing activities to geographically proximate countries. This works because shorter transit distances reduce exposure to maritime disruptions. Regional trade agreements created incentives for localized supply clusters. Labor cost differentials remained relevant but were weighed against transportation reliability and tariff exposure. Governments introduced industrial policies to attract strategic industries such as semiconductor fabrication. According to policy analyses, public subsidies influenced corporate location decisions significantly. The architecture of supply chains began reflecting a balance between global integration and regional consolidation. Environmental sustainability further reshaped corporate supply chain priorities. Carbon emissions from transportation and energy-intensive manufacturing attracted regulatory scrutiny. Firms established science-based targets to reduce greenhouse gas output across value chains. This works because measurement frameworks link environmental performance to operational decision-making. Life cycle assessments quantified emissions from raw material extraction to product disposal. The reason comprehensive accounting matters is that upstream suppliers often generate the majority of emissions. Companies invested in renewable energy sourcing and energy-efficient logistics fleets. According to sustainability research, transparent reporting enhanced investor confidence in long-term strategy. Supply chain design evolved to integrate ecological constraints alongside economic objectives. Artificial intelligence and automation continued transforming operational structures. Autonomous mobile robots improved warehouse productivity and safety outcomes. Advanced optimization algorithms recalculated routing decisions in response to real-time traffic conditions. This works because computational speed enables rapid adjustment to variable inputs. Supplier risk scoring models incorporated geopolitical data, weather patterns, and financial indicators. The reason predictive modeling matters is that early warning signals allow preventative action. Blockchain applications expanded traceability for food, pharmaceuticals, and luxury goods. Data interoperability standards emerged to facilitate cross-platform integration. Corporate supply chains increasingly resembled adaptive digital ecosystems layered upon global physical infrastructure. As corporations navigate this evolving landscape, supply chain design remains a continuous strategic process. Competitive advantage depends on aligning operational architecture with shifting market realities. Efficiency, resilience, sustainability, and digital capability now coexist within unified frameworks. Decision makers interpret quantitative models through organizational culture and leadership priorities. Long-term capital investments in infrastructure and technology shape performance for decades. Trade policy shifts, demographic change, and technological innovation will continue altering design parameters. Corporate supply chains reflect both deliberate planning and adaptive learning. The system remains in motion, shaped by forces that extend beyond any single firm and continuing to redefine how production and exchange are organized across the global economy. Modern supply chains operate across continents, time zones, and political systems, forming networks of extraordinary scale and complexity. What began centuries ago as regional trade routes has matured into tightly synchronized global systems that move components and finished goods with remarkable precision. In earlier chapters, production expanded, standardized, and dispersed geographically, creating deep interdependencies between firms and nations. These interdependencies brought efficiency and lower costs, but they also introduced new forms of vulnerability. A disruption in one location can ripple outward through ports, warehouses, factories, and retail networks within days. The structure resembles a web, where tension at one point subtly shifts the balance across the entire network. Risk is not an external anomaly in such systems but a structural feature embedded in their design. As globalization intensified during the late 20th century, the pursuit of efficiency often narrowed margins for error. By the early 21st century, resilience became as critical as speed and cost in strategic planning. The mechanism of risk propagation in global supply chains is rooted in specialization and synchronization. Firms concentrate production in regions that offer comparative advantages, reducing redundancy in favor of scale economies. This works because specialization lowers per-unit costs and enhances technical expertise within focused facilities. However, when production is concentrated, Any disruption in that location can halt output for multiple downstream firms. Inventory buffers, once common in earlier industrial systems, were reduced under lean management philosophies. The reason lean systems became dominant was the financial benefit of minimizing idle capital tied up in stock. Yet the reduction of buffers increases sensitivity to delays, whether caused by natural disasters, labor disputes, or regulatory shifts. According to studies published by the World Bank, trade integration magnifies both gains and vulnerabilities as countries deepen cross-border linkages. The system functions efficiently in stable conditions, but volatility reveals the trade-offs embedded within its architecture. Resilience, therefore, requires deliberate design choices that may partially offset pure efficiency. Historical disruptions have repeatedly exposed these vulnerabilities. By 2011, the earthquake and tsunami in Japan disrupted automotive and electronics supply chains worldwide. At the time, several critical components were produced by single specialized suppliers located within affected regions. Production halts in these facilities led to assembly line shutdowns in distant countries that depended on those inputs. By 2020, the COVID-19 pandemic generated simultaneous supply and demand shocks across nearly every major economy. Lockdowns constrained manufacturing output, while shifts in consumer behavior altered demand patterns unexpectedly. According to reports from the International Monetary Fund, global trade volumes contracted sharply during the early phases of the crisis before partially rebounding. These events did not create fragility from nothing, but they illuminated structural dependencies that had accumulated over decades. Each disruption reinforced the lesson that interconnected systems amplify both efficiency and exposure. Risk within supply chains can be categorized into operational, geopolitical, environmental, and financial dimensions. Operational risks include equipment failures, labor shortages, and logistical bottlenecks that interrupt routine flows. Geopolitical risks arise from trade disputes, sanctions, or regulatory changes that alter market access. Environmental risks encompass extreme weather events, resource scarcity, and long-term climate shifts that affect production zones. Financial risks involve currency volatility, credit constraints, and sudden changes in capital availability. The reason these categories matter is that mitigation strategies differ across each domain. Insurance instruments may offset financial losses, but they do not restore lost production capacity. Diversifying suppliers can reduce operational concentration, yet it may introduce coordination complexity. Effective resilience requires mapping these risks systematically and aligning countermeasures with specific vulnerabilities. Redundancy represents one of the oldest and most reliable strategies for managing uncertainty. Maintaining multiple suppliers for critical components ensures that the failure of one does not halt the entire chain. This works because parallel pathways provide alternative routes for materials and information. However, redundancy carries costs in the form of duplicated contracts, higher inventory levels, and reduced economies of scale. Firms must balance the expense of preparedness against the probability and magnitude of disruption. According to research from the Massachusetts Institute of Technology, diversified sourcing strategies can moderate shock transmission while preserving competitive performance. The challenge lies in determining which nodes in the network warrant redundancy and which can operate efficiently without it. Strategic assessment rather than uniform duplication becomes the guiding principle. Over time, companies increasingly use data analytics to identify high-risk nodes that justify additional safeguards. Resilience also depends on visibility across the network. Digital tracking technologies allow firms to monitor shipments, inventory levels, and production status in real time. The mechanism here involves integrating information systems across suppliers, logistics providers, and customers. This works because timely data enables rapid response to emerging disruptions before they escalate. Without visibility, firms may discover shortages only after assembly lines stop. The expansion of enterprise resource planning systems in the late 20th century laid the foundation for such integration. By the 2010s, cloud computing platforms further enhanced coordination across dispersed operations. According to the Organization for Economic Cooperation and Development, digitalization strengthens adaptive capacity when supported by standardized data protocols. Information flow, therefore, becomes as vital as physical movement in maintaining continuity. Resilience at the systemic level extends beyond individual firms to national and regional strategies. Governments increasingly evaluate critical supply chains in sectors such as semiconductors, pharmaceuticals, and energy. By 2021, several major economies launched initiatives to reassess dependence on foreign suppliers for strategic goods. At the time, policymakers framed resilience as a component of economic security rather than mere commercial efficiency. This shift reflected recognition that supply disruptions can carry social and political consequences. Public investment in domestic capacity, stockpiling programs, and trade diversification strategies became part of national agendas. According to analysis by the World Economic Forum, resilience planning requires collaboration between public and private actors. The interplay between market incentives and policy frameworks shapes the architecture of redundancy. As supply chains continue to evolve, the balance between efficiency and security remains a defining tension within the global system. Resilience in global supply chains increasingly depends on strategic diversification rather than simple duplication. Firms that once concentrated production in a single low-cost region now evaluate geographic spread as a protective measure. The reason diversification matters is that regional shocks rarely occur simultaneously across distant locations. Political instability in one country does not automatically coincide with environmental disruption in another. By distributing manufacturing and sourcing across multiple jurisdictions, companies reduce exposure to localized crises. This approach does not eliminate risk, but it dampens the intensity of any single disruption. According to research from the United Nations Conference on Trade and Development, regional production networks have grown alongside global ones, creating layered trade structures. These overlapping networks provide flexibility when long-distance routes become constrained. Diversification therefore functions as a structural hedge embedded directly into the architecture of production. Nearshoring and reshoring represent more specific expressions of this diversification trend. Nearshoring involves relocating production closer to primary consumer markets while maintaining cross-border efficiency. Reshoring brings previously outsourced production back to domestic territory. The mechanism behind both strategies is risk compression through distance reduction. Shorter transportation routes decrease transit times and reduce exposure to maritime choke points or port congestion. This works because fewer logistical steps mean fewer potential failure points. By 2022, several multinational firms announced partial reshoring plans in response to pandemic-related bottlenecks. According to analysis by the McKinsey & Company, companies increasingly weigh resilience metrics alongside labor cost differentials. The shift does not signal a retreat from globalization, but a recalibration of its geographic balance. Supply chains become more regionally anchored while remaining internationally connected. Inventory management practices have also evolved in response to recurring disruptions. For decades, just-in-time production minimized stock levels to enhance capital efficiency. The reason this model prevailed was its capacity to free cash and streamline operations. However, when transportation delays or supplier shutdowns occur, minimal inventories leave firms vulnerable. buffer stocks re-emerged as a strategic instrument after successive global shocks. Maintaining higher safety stock levels increases carrying costs, yet it provides time to adjust sourcing when disruptions arise. According to studies by the Harvard Business School, firms that balanced lean principles with selective buffers experienced faster recovery during crisis periods. The recalibration of inventory policy reflects a broader reassessment of acceptable trade-offs. Efficiency remains important, but continuity increasingly commands equal consideration. Technological integration strengthens resilience by enhancing predictive capacity. Advanced analytics allow firms to simulate supply disruptions and evaluate alternative scenarios before crises materialize. The mechanism involves aggregating data from suppliers, logistics providers, and market signals into unified forecasting models. This works because early warning indicators enable preemptive adjustments in procurement and distribution. Artificial intelligence tools identify anomalies in shipping times, order volumes, or commodity prices that may signal emerging stress. By the mid-2010s, predictive analytics platforms became common within large multinational enterprises. According to the Gartner, digital maturity correlates strongly with recovery speed after operational shocks. Technology does not remove uncertainty, but it reduces reaction time and improves decision quality under pressure. Financial resilience forms another critical dimension of supply chain stability. Access to credit and liquidity determines whether firms can absorb temporary revenue declines. During disruptions, smaller suppliers often face cash flow constraints that threaten their survival. Larger buyers increasingly provide financial support or early payment arrangements to stabilize vulnerable partners. This works because sustaining upstream suppliers preserves continuity downstream. Supply chain finance programs expanded significantly after the global financial crisis of 2008. According to data compiled by the Bank for International Settlements, structured trade finance instruments mitigate liquidity shortages during stress periods. Financial coordination thus complements physical redundancy in maintaining system integrity. Environmental risk has become a defining factor in long-term supply chain planning. Extreme weather events disrupt ports, highways, and production facilities with increasing frequency. Rising sea levels threaten coastal industrial zones that host major export hubs. This works because climate exposure compounds existing logistical vulnerabilities. Firms now conduct climate risk assessments when selecting factory sites and distribution centers. Renewable energy integration also influences supplier evaluation criteria. According to the Intergovernmental Panel on Climate Change, climate-related disruptions are projected to intensify over coming decades. Anticipating environmental volatility, therefore, becomes inseparable from resilience strategy. Geopolitical fragmentation adds another layer of complexity to supply chain governance. Trade tensions, export controls, and sanctions reshape flows of technology and raw materials. The reason geopolitical risk carries systemic weight is that policy shifts can occur rapidly and unpredictably. Companies monitor diplomatic developments as closely as commodity prices. Strategic goods such as semiconductors and rare earth minerals attract particular scrutiny. By 2023, several economies introduced screening mechanisms for foreign investment in critical industries. According to reports from the European Commission, regulatory coordination seeks to balance openness with security considerations. Supply chains thus reflect political alignments as much as economic efficiencies. Resilience ultimately emerges from the interaction of diversification, technology, finance, and governance. No single intervention guarantees continuity in an interconnected global system. Instead, layered safeguards distribute risk across multiple dimensions. Firms combine geographic spread, digital visibility, buffer inventories, and financial partnerships to reinforce stability. Governments contribute through infrastructure investment and policy coordination. This works because distributed responsibility reduces dependence on any singular protective mechanism. According to the World Trade Organization, sustained cooperation remains essential for preserving open yet secure trade networks. As global supply chains continue to adapt, resilience becomes an evolving process rather than a fixed design, shaped continuously by new shocks and structural change. Resilience in global supply chains increasingly depends on structural flexibility embedded at the design stage rather than improvised during crisis. Firms now approach network architecture as a dynamic system capable of reconfiguration under stress. Production lines are engineered to accommodate alternative inputs when primary components become unavailable. This works because modular design reduces dependence on uniquely customized parts that cannot be easily substituted. Standardized interfaces between components allow suppliers to be swapped with minimal technical disruption. The mechanism resembles interchangeable parts in early industrial manufacturing, but applied across continents and digital platforms. According to research from the Stanford University, modularity enhances adaptive capacity in complex production ecosystems. Flexibility, therefore, becomes a form of redundancy that does not always require duplicate facilities. It embeds optionality directly into the technical blueprint of goods and processes. Supplier relationships also evolve from transactional exchanges toward collaborative partnerships. Long-term contracts encourage shared investment in contingency planning and information transparency. The reason collaboration strengthens resilience is that trust reduces hesitation during emergencies. Suppliers that communicate openly about capacity constraints enable buyers to adjust procurement schedules before shortages intensify. Joint scenario planning exercises simulate disruptions and test response protocols. This works because rehearsed coordination reduces confusion when actual stress occurs. According to findings published by the London School of Economics, relational contracting improves performance stability in volatile environments. Supply chains cease to function merely as cost-minimizing mechanisms and become coordinated risk-sharing systems. The social dimension of economic exchange thus reasserts importance within technologically advanced networks. Transportation infrastructure remains a decisive factor in resilience outcomes. Ports, railways, highways, and air cargo hubs form the physical arteries of global trade. When congestion or closure occurs at major nodes, cascading delays follow. Diversifying transport routes reduces dependence on singular choke points. This works because alternative corridors absorb overflow when primary channels fail. By the early 2020s, attention focused on vulnerabilities surrounding critical maritime passages such as the Suez Canal. Temporary blockages demonstrated how narrow passages can disrupt billions of dollars in daily trade. Governments responded with renewed investment in port modernization and inland logistics networks. Infrastructure resilience therefore complements corporate diversification strategies at a macroeconomic level. Labor dynamics introduce another layer of systemic risk. Skilled workers operate machinery, manage logistics software, and maintain quality control across production stages. Strikes, health crises, or demographic shortages can impair throughput even when facilities remain intact. The mechanism here involves human capital concentration in specialized roles. Cross-training programs expand workforce versatility and reduce dependence on singular expertise. This works because employees capable of performing multiple tasks provide operational continuity during absences. According to data from the International Labor Organization, labor shortages in logistics and manufacturing intensified during global recovery phases. Workforce planning thus becomes inseparable from supply chain resilience. Stability depends not only on materials and machines, but also on coordinated human effort. Energy security further shapes production continuity in an interconnected economy. Manufacturing facilities rely on stable electricity and fuel supplies to sustain operations. Price volatility or supply interruption in energy markets transmits rapidly through cost structures. The reason energy diversification matters is that reliance on a single source magnifies exposure to geopolitical shocks. Renewable integration, local generation capacity, and diversified fuel contracts moderate this exposure. This works because distributed energy inputs prevent singular failures from halting entire production lines. According to assessments by the International Energy Agency, energy system resilience increasingly intersects with industrial competitiveness. Supply chain planning now incorporates power infrastructure as a strategic variable rather than a background assumption. Data security and cyber resilience have emerged as critical components of modern supply networks. Digital platforms coordinate orders, track shipments, and manage payments across global partners. Cyber attacks targeting logistics software or port management systems can disrupt physical trade without damaging tangible assets. The mechanism involves unauthorized access that corrupts or disables information flows. This works because contemporary supply chains depend on synchronized data exchanges for scheduling and inventory control. By the late 2010s, ransomware incidents affecting shipping companies and manufacturers highlighted digital vulnerabilities. According to the Cybersecurity and Infrastructure Security Agency, integrated cyber defense frameworks reduce systemic exposure. Technological resilience must therefore extend beyond predictive analytics to encompass defensive architecture. National stockpiling strategies illustrate how public policy reinforces private resilience measures. Governments maintain reserves of essential goods such as medical supplies, food staples, and strategic minerals. The reason stockpiling persists despite high carrying costs is the recognition that markets alone may not respond quickly during emergencies. Public reserves provide a buffer that stabilizes critical sectors while commercial supply adjusts. This works because temporary substitution buys time for production reallocation and logistical rerouting. By 2022, several countries expanded medical stockpiles in response to pandemic shortages. According to reports by the World Health Organization, coordinated procurement and reserve management enhance preparedness for cross-border crises. Public and private redundancy thus converge within broader resilience ecosystems. Resilience ultimately reflects an evolving equilibrium between efficiency and precaution. Global supply chains cannot eliminate uncertainty, but they can distribute its impact across diversified structures. Firms evaluate exposure through stress testing, scenario modeling, and continuous monitoring of geopolitical and environmental trends. The mechanism of adaptation relies on feedback loops that integrate new information into planning cycles. This works because learning from disruption transforms isolated shocks into systemic knowledge. As complexity deepens, resilience becomes a continuous process rather than a static objective. Networks adjust incrementally, embedding safeguards while preserving competitive advantage. The architecture of global trade continues to shift under pressure, balancing openness with security as economic integration advances into increasingly uncertain terrain. The architecture of global supply chains has steadily shifted from fragmented trade relationships to deeply integrated production networks. Earlier eras depended on discrete exchanges between exporters and importers, each transaction largely self-contained. Over time, multinational firms began to coordinate production stages across multiple countries, linking factories, suppliers, and logistics providers into unified systems. By the late 20th century, Improvements in telecommunications and transportation reduced the cost of coordination across distance. Containers standardized cargo movement, while digital communication synchronized decisions in real time. The supply chain ceased to be a linear path and became instead a complex web of interdependent nodes. Production no longer belonged to a single place, but unfolded across continents according to strategic calculation. Integration required not only infrastructure, but also shared standards, contracts, and data systems that allowed firms to operate as if borders imposed minimal friction. The result was an economic landscape defined by distributed manufacturing and coordinated specialization. By the 1980s, trade liberalization accelerated this integration. Agreements such as the World Trade Organization established frameworks that reduced tariffs and formalized dispute resolution. At the time, policymakers viewed cross-border production as a pathway to efficiency and growth. The fall of the Berlin Wall symbolized the opening of new labor markets and industrial regions. By the early 1990s, manufacturers were allocating tasks based on comparative cost advantages across Eastern Europe and Asia. China's economic reforms, formalized under the leadership of Deng Xiaoping, encouraged foreign direct investment and export-oriented production. According to trade data compiled by the World Bank, global merchandise exports expanded rapidly during this period. These historical developments converged to create conditions favorable to integrated global production. Firms increasingly designed products with the expectation that components would cross borders multiple times before completion. The mechanism behind integrated production rests on the strategic fragmentation of tasks. Companies divide complex manufacturing processes into discrete stages, each located where it can be performed most efficiently. The reason this approach reduces costs lies in differential wage levels, regulatory environments, and industrial capabilities. This works because transportation and coordination expenses have fallen relative to labor and capital differentials. Digital systems track inventory across thousands of suppliers, enabling firms to align output with demand signals. Standardized components ensure compatibility between factories separated by oceans. Financial instruments hedge currency risk and stabilize transactions. The integration extends beyond physical goods to encompass information flows and capital allocation. Production planning software aggregates data from sales forecasts, shipping schedules, and supplier capacities into unified dashboards. Narrative examples illustrate how a single consumer product can embody global integration. A smartphone may incorporate semiconductors fabricated in Taiwan, memory chips assembled in South Korea, and design specifications generated in California. Final assembly might occur in coastal China, while logistics hubs in Singapore coordinate distribution to European and American markets. Each component supplier operates within strict quality standards and synchronized timelines. Shipping containers move between ports according to prearranged schedules, minimizing idle inventory. Retailers receive goods just in time for seasonal demand peaks. This distributed choreography depends on constant communication between firms that may never share a common language or legal system. Yet standardized documentation and shared digital platforms create functional alignment. The finished product appears seamless, though its creation spans dozens of jurisdictions and industrial clusters. According to studies published by the Organization for Economic Cooperation and Development, global value chains account for a substantial share of international trade. These chains measure not only the exchange of final goods, but the value added at each production stage. Research from the International Monetary Fund indicates that integration increases productivity through specialization and knowledge transfer. The reason productivity rises lies in firms concentrating on core competencies while outsourcing ancillary tasks. This works because specialization fosters cumulative expertise and capital deepening. Data sharing across borders accelerates learning cycles and standard adoption. Financial markets reward firms capable of coordinating complex supplier networks. Over time, integrated production reshapes corporate structure itself, favoring asset-light models that rely on partnerships rather than vertical ownership. Historical precedent for integration can be traced to earlier multinational enterprises, yet the scale expanded dramatically in the late 20th century. By 2001, China's accession to the World Trade Organization further institutionalized its role within global manufacturing networks. At the time, foreign firms increased investment in coastal industrial zones. Container traffic through ports such as Shanghai and Rotterdam multiplied within a decade. Advances in enterprise resource planning software during the 1990s provided firms with integrated digital oversight. These systems allowed executives to monitor production metrics across multiple countries simultaneously. The historical trajectory reveals a steady layering of legal agreements, infrastructure, and digital coordination. Integrated production emerged not from a single innovation, but from cumulative institutional development. The analytical structure of integrated global production depends on interdependence. The mechanism of just-in-time manufacturing reduces inventory buffers and increases responsiveness. The reason firms adopt this model lies in cost reduction and capital efficiency. This works because inventory represents tied-up capital and storage expense. However, interdependence also amplifies vulnerability when disruptions occur. A delayed shipment of microchips can halt automobile assembly lines thousands of miles away. Financial hedging mitigates some uncertainty, yet physical bottlenecks remain material constraints. Risk management strategies therefore diversify suppliers and incorporate redundancy into logistics planning. Integration requires balancing efficiency with resilience in a constantly shifting geopolitical landscape. As the 21st century progressed, integrated production became the default architecture of global commerce. Firms designed supply networks assuming stable trade relations and predictable transit corridors. Investment flowed into ports, railways, and data infrastructure to sustain these assumptions. Digital platforms synchronized procurement, manufacturing, and distribution in real time. Cross-border capital mobility financed expansion into emerging markets. The visible outcome was an unprecedented availability of consumer goods at relatively stable prices. Beneath that surface, however, the network operated through dense layers of coordination that depended on political stability and technological reliability. The global factory functioned as a distributed organism, sensitive to shocks yet capable of remarkable output when conditions aligned. Its complexity suggested both the culmination of centuries of logistical evolution and the beginning of a new phase defined by adaptation to uncertainty. Integrated global production depends on invisible layers of coordination that extend far beyond the factory floor. Firms align procurement schedules with shipping timetables and warehouse capacities across multiple continents. Software platforms aggregate real-time data on orders, inventory levels, and supplier performance. The mechanism of coordination relies on standardized digital protocols that allow disparate systems to communicate seamlessly. The reason this structure functions at scale lies in shared technical standards adopted across industries. This works because compatibility reduces translation costs between systems and minimizes human intervention. Cloud computing enables centralized oversight while preserving local operational autonomy. Managers in one country can adjust production targets in another within seconds. The integration of data flows becomes as important as the movement of physical goods. In this environment, efficiency arises from synchronization rather than simple cost minimization. By the early 2000s, enterprise software firms such as SAP and Oracle Corporation provided multinational corporations with comprehensive resource planning tools. At the time, these systems unified accounting, logistics, and procurement under a single digital architecture. By 2010, cloud-based services further reduced the cost of implementing complex coordination platforms. According to reports from the United Nations Conference on Trade and Development, foreign direct investment flows increasingly targeted supply chain infrastructure and digital services. Studies show that firms adopting integrated software platforms achieved measurable reductions in lead times and inventory holdings. These historical shifts reinforced the trend toward global interdependence. Governments invested in fiber optic networks and port automation to remain competitive within these systems. The cumulative effect was a tightening of the operational web that connected suppliers, manufacturers, and distributors. The analytical core of integrated production lies in modularization. Companies design products as assemblies of interchangeable components that can be sourced from specialized producers. The mechanism reduces complexity by isolating tasks into defined units with clear specifications. The reason modularization supports global integration is that it limits the need for constant redesign across the entire system. This works because each supplier focuses on a narrow domain of expertise while adhering to standardized interfaces. Quality control protocols verify compliance before components move to the next stage. Certification bodies audit facilities to ensure consistency across borders. Financial contracts allocate responsibility for delays or defects with explicit clarity. Through modular design, firms transform geographical dispersion into a manageable organizational structure. Consider the automotive industry as an illustration of distributed specialization. An engine control unit may be designed in Germany, fabricated in Malaysia, and programmed in Mexico. Steel components originate from mills in South Korea, while electronic sensors are sourced from Japan. Final assembly plants in the United States or Eastern Europe integrate these parts into completed vehicles. Each tier of suppliers operates under performance metrics tied to delivery precision and defect rates. Logistics providers coordinate multimodal transport across sea, rail, and road corridors. Inventory buffers remain minimal to preserve capital efficiency. The finished automobile represents the culmination of synchronized contributions from dozens of firms. Integration transforms geographic distance into a sequence of timed operations. According to analysis from the McKinsey & Company, value chains in advanced manufacturing often span more than 20 countries. Research published by the Harvard Business School indicates that firms embedded in dense supplier networks exhibit higher innovation rates. The reason innovation accelerates lies in knowledge diffusion across interconnected partners. This works because exposure to diverse production techniques fosters incremental improvement. Shared technical standards allow rapid adoption of new components without redesigning entire systems. Data analytics measure supplier performance and highlight inefficiencies in near real time. Investors evaluate companies based on their ability to manage complex global networks effectively. Integration thus becomes both an operational strategy and a signal of organizational competence. Historical disruptions have periodically tested this architecture. The global financial crisis of 2008 exposed vulnerabilities in trade finance and demand forecasting. At the time, sudden contractions in consumer spending reverberated across supplier tiers. Factories reduced output in response to declining orders, affecting upstream raw material producers. Recovery required coordinated stimulus measures and renewed credit flows. More recently, the COVID-19 pandemic strained transportation corridors and temporarily closed manufacturing hubs. According to the World Health Organization, Public health measures disrupted labor availability and cross-border mobility. These events demonstrated that efficiency-oriented integration carries systemic risk. Firms began reassessing the balance between cost optimization and resilience. The mechanism of resilience involves diversification and strategic redundancy. Companies identify alternative suppliers in different geographic regions to reduce concentration risk. The reason diversification enhances stability lies in reducing exposure to localized disruptions. This works because independent nodes in the network can compensate for temporary failures elsewhere. Digital twins simulate supply chain scenarios to evaluate potential bottlenecks before they materialize. Governments encourage domestic production of critical goods through targeted incentives. Insurance markets expand coverage for supply chain interruption risks. Financial reserves buffer firms against temporary revenue shocks. Integration evolves from a purely efficiency-driven model toward a hybrid structure that incorporates risk management as a core principle. As integrated global production matures, its contours reflect both technological advancement and institutional adaptation. Firms continue refining coordination tools while negotiating trade agreements and regulatory frameworks. Investment in automation and artificial intelligence further compresses response times within complex networks. Emerging economies seek participation by upgrading infrastructure and workforce capabilities. Cross-border collaboration remains central to sustaining productivity growth. At the same time, geopolitical tensions introduce new variables into strategic planning. Supply chain mapping becomes a routine executive function rather than a specialized analytical task. The global production system operates as a layered structure of contracts, data streams, and physical flows. Its continued evolution depends on the capacity of institutions and enterprises to recalibrate integration in response to shifting economic and political conditions. Integrated global production has reached a level of complexity where strategic planning extends years into the future. Corporations model demand projections across regions, aligning capital expenditure with anticipated consumption patterns. Semiconductor fabrication plants, pharmaceutical facilities, and advanced robotics factories require multi-billion-dollar investments that assume stable cross-border coordination. The mechanism of long-term integration depends on contractual commitments between suppliers and anchor firms. The reason these commitments matter lies in the scale of sunk costs embedded in specialized equipment. This works because dedicated facilities cannot easily pivot to alternative clients without substantial reconfiguration. Governments often support such investments through tax incentives and infrastructure guarantees. Capital markets provide financing based on expected global demand trajectories. Integrated production therefore rests on shared expectations about the durability of economic openness. By 2015, digital platforms such as Amazon and Alibaba Group had redefined the interface between producers and consumers. At the time, their logistics networks demonstrated how data analytics could anticipate purchasing behavior and adjust inventory flows accordingly. According to reports from the World Economic Forum, platform-based coordination increased transparency within global supply chains. Studies show that real-time tracking systems reduced shipment delays and improved forecasting accuracy. The expansion of 5G telecommunications further accelerated machine-to-machine communication within industrial environments. By the early 2020s, sensors embedded in shipping containers transmitted location and temperature data continuously. These historical developments deepened the informational integration that underpins physical production. Digital oversight became inseparable from material movement. The analytical dimension of integrated production increasingly incorporates automation. Robotics perform repetitive assembly tasks with precision and consistency. The mechanism reduces reliance on manual labor for standardized operations. The reason automation complements global integration lies in its compatibility with modular design principles. This works because programmable machines can replicate identical processes across facilities in different countries. Artificial intelligence systems analyze performance metrics to identify inefficiencies in real time. Predictive maintenance algorithms reduce downtime by forecasting equipment failure before it occurs. Automated warehouses coordinate picking and packing through algorithmic routing. Integration thus extends beyond human coordination to include synchronized machine networks. Consider the semiconductor industry as a concentrated example of global interdependence. Design firms in the United States create chip architectures that are fabricated by foundries in Taiwan. Specialized equipment manufacturers in the Netherlands supply lithography machines essential to advanced production. Chemical inputs originate from Japan and Germany, while assembly and testing occur in Southeast Asia. Each segment depends on technical expertise that has accumulated over decades. Logistics corridors must maintain temperature control and contamination safeguards during transit. Financial contracts allocate risk across multiple tiers of suppliers. The finished microchip embodies a collaboration that spans continents and regulatory regimes. Integrated production in this sector reveals how specialization and trust converge in highly technical domains. According to research from the International Trade Center, small and medium-sized enterprises increasingly participate in global value chains through digital marketplaces. Studies published by the Brookings Institution indicate that digital integration lowers entry barriers for niche suppliers. The reason access expands lies in transparent pricing and standardized documentation. This works because online platforms match buyers and sellers without requiring extensive physical presence abroad. Secure payment systems reduce transaction risk across jurisdictions. Rating mechanisms create reputational incentives that reinforce reliability. Integration therefore diffuses beyond multinational corporations to encompass a broader ecosystem of firms. Global production becomes more inclusive while remaining structurally interconnected. Historical patterns suggest that integration evolves in response to geopolitical pressures. Trade tensions during the late 2010s prompted some firms to reassess concentration in specific regions. At the time, tariffs and export controls introduced uncertainty into previously stable arrangements. Governments enacted industrial policies aimed at reshoring critical manufacturing capacity. Supply chain mapping exercises identified dependencies in sectors such as medical equipment and energy storage. By 2022, strategic stockpiles and regional trade agreements reflected a partial recalibration of integration strategies. These adjustments did not dismantle global production, but modified its configuration. Historical precedent indicates that supply networks adapt rather than disappear. The mechanism of adaptation involves regionalization layered upon global coordination. Firms maintain core international partnerships while developing secondary hubs closer to end markets. The reason regional clusters emerge lies in balancing efficiency with political risk mitigation. This works because shorter transit distances reduce exposure to border disruptions. Data analytics evaluate trade-offs between cost savings and resilience metrics. Environmental considerations also influence network design, as carbon accounting becomes embedded in corporate reporting. Renewable energy investments reshape the geography of industrial activity. Integration increasingly accounts for sustainability alongside profitability. As integrated global production continues to evolve, it reflects the cumulative interplay of technology, policy, and corporate strategy. The system operates through intricate feedback loops connecting consumer demand, capital allocation, and industrial capability. Digital infrastructure binds these elements into a coherent operational framework. Political decisions alter incentives and redirect investment flows. Firms respond by recalibrating supplier portfolios and production footprints. Innovation persists within this dynamic environment, reinforcing specialization while accommodating new constraints. The global factory remains distributed yet coordinated, resilient yet interdependent. Its trajectory suggests an ongoing negotiation between openness and security, efficiency and stability, as economic actors navigate an increasingly complex world.